Section number 1
of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. Introduction. In a way, nuclear energy has been serving man as long as he has existed. It has served all of life. It has flooded the earth for billions of years. The sun, you see, is a vast nuclear engine, and the warmth and light that the sun radiates is the product of nuclear energy. In order for man to learn to produce and control nuclear energy himself, however, something that did not take place until this century, 3 lines of investigation, atoms, electricity, and energy, had to develop and meet. We will begin with atoms. Atomic weights. As long ago as ancient Greek times, there were men who suspected that all matter consisted of tiny particles which were far too small to see. Under ordinary circumstances, they could not be divided into anything smaller, and they were called atoms, from a Greek word meaning indivisible. It was not until 1808, however, that this atomic theory was really put on a firm foundation. In that year, the English chemist John Dalton, 1766 to 1844, published a book in which he discussed atoms in detail. Every element, he suggested, was made up of its own type of atoms. The atoms of one element were different from the atoms of every other element. The chief difference between the various atoms lay in their mass or weight. Dalton was the first to try to determine what these masses might be. He could not work out the actual masses in ounces or grams, for atoms were far too tiny to weigh with any of his instruments. He could, however, determine their relative weights, that is, how much more massive one kind of atom might be than another. For instance, he found that a quantity of hydrogen gas invariably combined with 8 times its own mass of oxygen gas to form water. He guessed that water consisted of combinations of 1 atom of hydrogen and 1 atom of oxygen. A combination of atoms is called a molecule, from a Greek word meaning a small mass, and so hydrogen and oxygen atoms can be said to combine to form a water molecule. To account for the difference in the masses of the combining gases, Dalton decided that the oxygen atom was 8 times as massive as the hydrogen atom. If he set the mass of the hydrogen atom at 1, just for convenience, then the mass of the oxygen atom ought to be set at 8. These comparative or relative numbers were said to be atomic weights, so that what Dalton was suggesting was that the atomic weight of hydrogen was 1 and the atomic weight of oxygen was 8. By noting the quantity of other elements that combined with a fixed mass of oxygen or of hydrogen, Dalton could work out the atomic weights of these elements as well. Dalton's idea was right, but his details were wrong in some cases. For instance, on closer examination, it turned out that the water molecule was composed of 1 oxygen atom and 2 hydrogen atoms. For this reason, the water molecule may be written H2O, where the H is the chemical symbol for a hydrogen atom and O for an oxygen atom. It is still a fact that a quantity of hydrogen combines with 8 times its mass of oxygen, so the single oxygen atom must be 8 times as massive as 2 hydrogen atoms taken together. The oxygen atom must therefore be 16 times as massive as a single hydrogen atom. If the atomic weight of hydrogen is 1, then the atomic weight of oxygen is 16. At first, it seemed that the atomic weights of the various elements were whole numbers, and that hydrogen was the lightest one. It made particular sense, then, to consider the atomic weight of hydrogen as 1, because that made all the other atomic weights as small as possible and therefore easy to handle. The Swedish chemist Jan Jacob Berzelius, 1779 to 1848, continued Dalton's work and found that elements did not combine in quite such simple ratios. A given quantity of hydrogen actually combined with a little bit less than 8 times its mass of oxygen. Therefore, if the atomic weight of hydrogen were considered to be 1, the atomic weight of oxygen would have to be not 16, but 15.87. As it happens, oxygen combines with more elements and more easily than hydrogen does. The ratio of its atomic weight to that of other elements is also more often a whole number. In working out the atomic weight of elements, it was therefore more convenient to set the atomic weight of oxygen at a whole number than that of hydrogen. Berzelius did this, for instance, in the table of atomic weights he published in 1828. At first he called the atomic weight of oxygen 100. Then he decided to make the atomic weights as small as possible, without allowing any atomic weight to be less than 1. For that reason, he set the atomic weight of oxygen at exactly 16, and in that case the atomic weight of hydrogen had to be placed just a trifle higher than 1. The atomic weight of hydrogen became 1.008. This system was retained for nearly a century and a half. Throughout the 19th century, chemists kept on working out atomic weights more and more carefully. By the start of the 20th century, most elements had their atomic weights worked out to 2 decimal places, sometimes 3. A number of elements had atomic weights that were nearly whole numbers on the oxygen equals 16 standard. The atomic weight of aluminum was just about 27, that of calcium was almost 40, that of carbon almost 12, that of gold almost 197, and so on. On the other hand, some elements had atomic weights that were far removed from whole numbers. The atomic weight of chlorine was close to 35.5, that of copper 63.5, that of iron 55.8, that of silver 107.9, and so on. Throughout the 19th century, chemists did not know why so many atomic weights were whole numbers, while others were not. They simply made their measurements and recorded what they found. For an explanation, they had to wait for a line of investigation into electricity to come to fruition. Electricity, units of electricity. Through the 18th century, scientists had been fascinated by the properties of electricity.
Electricity seemed at the time to be a very fine fluid that could extend through ordinary matter without taking up any room.
Electricity did more than radiate through matter, however. It also produced important changes in matter. In the first years of the 19th century, it was found that a current of electricity could cause different atoms or different groups of atoms to move in opposite directions through a liquid in which they were dissolved. The English scientist Michael Faraday, 1791 to 1867, noted in 1832 that a given quantity of electricity seemed to liberate the same number of atoms of a variety of different elements. In some cases, though, it liberated just half the expected number of atoms, or even in a few cases, just a third. Scientists began to speculate that electricity, like matter, might consist of tiny units. When electricity broke up a molecule, perhaps a unit of electricity attached itself to each atom. In that case, the same quantity of electricity, containing the same number of units, would liberate the same number of atoms. In the case of some elements, each atom could attach 2 units of electricity to itself, or perhaps even 3. When that happened, a given quantity of electricity would liberate only 1/2 or only 1/3 the usual number of atoms. Thus, 18 units of electricity would liberate 18 atoms if distributed 1 to an atom, only 9 atoms if distributed 2 to an atom, and only 6 atoms if distributed 3 to an atom. It was understood at the time that electricity existed in 2 varieties, which were called positive and negative. It appeared that if an atom attached a positive unit of electricity to itself, it would be pulled in one direction through the solution by the voltage. If it attached a negative unit of electricity to itself, it would be pulled in the other direction. The units of electricity were a great deal more difficult to study than the atomic units of matter, and throughout the 19th century they remained elusive. In 1891, though, the Irish physicist George Johnstone Stoney, 1826 to 1911, suggested that the supposed unit of electricity be given a name at least. He called the unit an electron. Cathode rays. An electric current flows through a closed circuit of some conducting material, such as metal wires. It starts at one pole of a battery or of some other electricity-generating device and ends at the other. The 2 poles are the positive pole, or anode, and the negative pole, or cathode. If there is a break in the circuit, the current will usually not flow at all. If, however, the break is not a large one, and the current is under a high driving force, which is called the voltage, then the current may leap across the break. If 2 ends of a wire making up part of a broken circuit are brought close to each other with nothing but air between, a spark may leap across the narrowing gap before they actually meet, and while it persists, the current will flow despite the break. The light of the spark and the crackling sound it makes are the results of the electric current interacting with molecules of air and heating them. Neither the light nor the sound is the electricity itself. In order to detect the electricity, the current ought to be forced across a gap containing nothing, not even air. In order to do that, wires would have to be sealed into a glass tube from which all or almost all the air was withdrawn. This was not easy to do, and it was not until 1854 that Heinrich Giesler, 1814 to 1879, a German glassblower and inventor, accomplished this feat. The wires sealed into such a Giesler tube could be attached to the poles of an electric generator, and if enough voltage was built up, the current would leap across the vacuum. Such experiments were first performed by the German physicist Julius Plücker, 1801 to 1868. In 1858 he noticed that when the current flowed across the vacuum, there was a greenish glow about the wire that was attached to the cathode of the generator. Others studied this glow, and finally the German physicist Eugene Goldstein, 1850 to 1931, decided in 1876 that there were rays of some sort beginning at the wire, attached to the negatively charged cathode, and ending at the part of the tube opposite the cathode. He called them cathode rays. These cathode rays, it seemed, might well be the electric current itself, freed from the metal wires that usually carried it. If so, determining the nature of the cathode rays might reveal a great deal about the nature of the electric current. Were cathode rays something like light, and were they made up of tiny waves? Or were they a stream of particles possessing mass? There were physicists on each side of the question. By 1885, however, the English physicist William Crookes, 1832 to 1919, showed that cathode rays could be made to turn a small wheel when they struck that wheel on one side. This seemed to show that the cathode rays possessed mass and were a stream of atom-like particles. rather than a beam of massless light. Furthermore, Crookes showed that the cathode rays could be pushed sideways in the presence of a magnet. This effect, when current flows in a wire, is what makes a motor work. This meant that, unlike either light or ordinary atoms, the cathode rays carried an electric charge. This view of the cathode rays as consisting of a stream of electrically charged particles was confirmed by another English physicist, Joseph John Thomson, 1856 to 1940. In 1897, he showed that the cathode rays could also be made to take a curved path in the presence of electrically charged objects. The particles making up the cathode rays were charged with negative electricity, judging from the direction in which they were made to curve by electrically charged objects. Thomson had no hesitation in maintaining that these particles carried the units of electricity that Faraday's work had hinted at. Eventually, Stoney's name for the units of electricity was applied to the particles that carried those units. The cathode rays, in other words, were considered to be made up of streams of electrons, and Thomson is usually given the credit for having discovered the electron. The extent to which cathode rays curved in the presence of a magnet or electrically charged objects depended on the size of the electric charge on the electrons and on the mass of the electrons. Ordinary atoms could be made to carry an electric charge, and, by comparing their behavior with those of electrons, some of the properties of electrons could be determined. There were, for instance, good reasons to suppose that the electron carried a charge of the same size as one that a hydrogen atom could be made to carry. The electrons, however, were much easier to pull out of their straight-line path than the charged hydrogen atom was. The conclusion drawn from this was that the electron had much less mass than the hydrogen atom. Thomson was able to show, indeed, that the electron was much lighter than the hydrogen atom, which was the lightest of all the atoms. Nowadays, we know the relationship quite exactly. We know that it would take 1,837.11 electrons to possess the mass of a single hydrogen atom. The electron is therefore a subatomic particle, the first of this sort to be discovered. In 1897, then, two types of mass-containing particles were known. There were the atoms which made up ordinary matter, and the electrons which made up electric current. Radioactivity. Was there a connection between these two sets of particles, atoms and electrons? In 1897, when the electron was discovered, a line of research that was to tie the two kinds of particles together had already begun. In 1895, the German physicist Wilhelm Conrad Röntgen, 1845 to 1923, was working with cathode rays. He found that if he made the cathode rays strike the glass at the other end of the tube, a kind of radiation was produced. This radiation was capable of penetrating glass and other matter. Röntgen had no idea as to the nature of the radiation, and so he called it X-rays. This name, containing the X for unknown, was retained even after physicists worked out the nature of X-rays and found them to be light-like radiation made up of waves much shorter than those of ordinary light. At once, physicists became fascinated with X-rays and began searching for them everywhere. One of those involved in the search was the French physicist Antoine-Henri Becquerel, 1852 to 1908. A certain compound, potassium uranyl sulfate, glowed after being exposed to sunlight, and Becquerel wondered if this glow, like the glow on the glass in Röntgen's X-ray tube, contained X-rays. It did, but while investigating the problem in 1896, Becquerel found that the compound was giving off invisible, penetrating X-ray-like radiation continually, whether it was exposed to sunlight or not. The radiation was detected because it would fog a photographic plate, just as light would. What's more, the radiation would fog the plate even if the plate were wrapped in black paper, so that it could penetrate matter just as X-rays could. Others, in addition to Becquerel, were soon investigating the new phenomenon. In 1898, the Polish, later French physicist Marie Sklodowska-Curie, 1867 to 1934, showed that it was the uranium atom that was the source of the radiation, and that any compound containing the uranium atom would give off these penetrating rays. Until then, uranium had not been of much interest to chemists.
It was a comparatively rare metal that was first discovered in 1789 by the German chemist Martin Heinrich Klaproth, 1743 to 1817.
It had no particular uses and remained an obscure element. As chemists learned to work out the atomic weights of the various elements, they found, however, that of the elements then known, uranium had the highest atomic weight of all, 238. Once uranium was discovered to be an endless source of radiation, it gained interest that has risen ever since. Madame Curie gave the name radioactivity to this phenomenon of continuously giving off rays. Uranium was the first element found to be radioactive. It did not remain alone, however. It was soon shown that thorium was also radioactive. Thorium, which had been discovered in 1829 by Berzelius, was made up of atoms that were the second most massive known at the time. Thorium's atomic weight is 232. But what was the mysterious radiation emitted by uranium and thorium? Almost at once it was learned that whatever the radiation was, it was not uniform in properties. In 1899, Becquerel and others showed that, in the presence of a magnet, some of the radiation swerved in a particular direction. Later it was found that a portion of it swerved in the opposite direction. Still another part didn't swerve at all, but moved on in a straight line. The conclusion was that uranium and thorium gave off three kinds of radiation. One carried a positive charge of electricity, one a negative charge, and one no charge at all. The New Zealand-born physicist Ernest Rutherford, 1871 to 1937, called the first two kinds of radiation alpha rays and beta rays, after the first two letters of the Greek alphabet. The third was soon called gamma rays, after the third letter. The gamma rays eventually turned out to be another light-like form of radiation, with waves even shorter than those of X-rays. The alpha rays and beta rays, which carried electric charges, seemed to be streams of charged particles, alpha particles and beta particles, just as the cathode rays had turned out to be. In 1900, indeed, Becquerel studied the beta particles and found them to be identical in mass and charge with electrons. They were electrons. By 1906, Rutherford had worked out the nature of the alpha particles. They carried a positive charge that was twice as great as the electron's negative charge. If an electron carried a charge that could be symbolized as a minus sign, then the charge of the alpha particle was 2 plus signs. Furthermore, the alpha particle was much more massive than the electron. It was, indeed, as massive as a helium atom, the second lightest known atom, and 4 times as massive as a hydrogen atom. Nevertheless, the alpha particle can penetrate matter in a way which atoms cannot, so that it seems much smaller in diameter than atoms are. The alpha particle, despite its mass, is another subatomic particle. Here, then, is the meeting point of electrons and of atoms, the particles of electricity and of matter. Ever since Dalton had first advanced the atomic theory over a century earlier, chemists had assumed that atoms were the fundamental units of matter. They had assumed atoms were as small as anything could be, and that they could not possibly be broken up into anything smaller. The discovery of the electron, however, had shown that some particles, at least, might be far smaller than any atom. Then the investigations into radioactivity had shown that atoms of uranium and thorium spontaneously broke up into smaller particles, including electrons and alpha particles. It would seem, then, that atoms of these elements, and presumably of all elements, were made up of still smaller particles, and that among these particles were electrons. The atom had a structure, and physicists became interested in discovering exactly what that structure was. The structure of the atom. Since radioactive atoms gave off either positively charged particles or negatively charged particles, it seemed reasonable to assume that atoms generally were made up of both types of electricity. Furthermore, since the atoms in matter generally carried no charge at all, the normal neutral atom must be made up of equal quantities of positive charge and negative charge. It turned out that only radioactive atoms, such as those of uranium and thorium, gave off positively charged alpha particles. Many atoms, however, that were not radioactive could be made to give off electrons. In 1899, Thomson showed that certain perfectly normal metals, with no trace of radioactivity, gave off electrons when exposed to ultraviolet light. This is called the photoelectric effect. It was possible to suppose, then, that the main structure of the atom was positively charged and generally immovable, and that there were also present light electrons, which could easily be detached. Thomson had suggested as early as 1898 that the atom was a ball of matter carrying a positive charge, and that individual electrons were stuck throughout its substance like raisins in pound cake. If something like the Thomson view were correct, then the number of electrons, each with 1 unit of negative electricity, would depend on the total size of the positive charge carried by the atom. If the charge were +5, there would have to be 5 electrons present to balance that. The total charge would then be 0, and the atom as a whole would be electrically neutral. If, in such a case, an electron were removed, the atomic charge of +5 would be balanced by only 4 electrons with a total charge of -4. In that case, the net charge of the atom as a whole would be +1. On the other hand, if an extra electron were forced into an atom, the charge of +5 would be balanced by 6 electrons with a total charge of -6, and the net charge of the atom as a whole would be -1. Such electrically charged atoms were called ions, and their existence had been suspected since Faraday's day. Faraday had known that atoms had to travel through a solution under the influence of an electric field to account for the way in which metals and gases appeared at the cathode and anode. It was he who first used the term ion from a Greek word meaning traveler. The word had been suggested to him by the English scholar William Whewell, 1794 to 1866. In 1884, the Swedish chemist Svante August Arrhenius, 1859 to 1927, had first worked out a detailed theory based on the suggestion that these ions were atoms or groups of atoms that carried an electric charge. By the close of the 19th century, then, Arrhenius' suggestion seemed correct. There were positive ions made up of atoms or groups of atoms from which one or more of the electrons within the atoms had been removed.
There were negative ions made up of single atoms or of groups of atoms to which one or more extra electrons had been added.
Although Thomson's model of the atom explained the existence of ions and the fact that atoms could give off electrons or absorb them, it was not satisfactory in all ways. Further investigations yielded results not compatible with the raisins in the pound cake notion. In 1906, Rutherford began to study what happened when massive subatomic particles, such as alpha particles, passed through matter. When alpha particles passed through a thin film of gold, for instance, they raced through, for the most part, as though nothing were there. The alpha particles seemed to push the light electrons aside and act as though the positively charged main body of the atom that Thomson had pictured was not solid, but was soft and spongy. The only trouble was that every once in a while an alpha particle seemed to strike something in the gold film and bounce to one side. Sometimes it even bounced directly backward. It was as though somewhere in each atom there was something at least as massive as the alpha particle. How large was this massive portion of the atom? It couldn't be very large, for if it were, the alpha particles would hit it frequently. Instead, the alpha particles made very few hits. This meant the massive portion was very small, and that most alpha particles tore through the atom without coming anywhere near it. By 1911, Rutherford announced his results to the world. He suggested that just about all of the mass of the atom was concentrated into a very tiny, positively charged nucleus at its center. The diameter of the nucleus was only about 1/10,000th the diameter of the atom. All the rest of the atom was filled with the very light electrons. According to Rutherford's notion, the atom consisted of a single, tiny, positively charged lead shot at the center of a foam of electrons. It was Thomson's notion in reverse. Still, the nucleus carried a positive charge of a particular size and was balanced by negatively charged electrons. Rutherford's model of the atom explained the existence of ions just as easily as Thomson's did, and it explained more besides. For instance, if all the electrons are removed so that only the nucleus remains, this nucleus is as massive as an atom, but is so tiny in size that it can penetrate matter. The alpha particle would be a bare atomic nucleus from this point of view. Rutherford's model of the nuclear atom is still accepted today. Atomic numbers. Since the atom consisted of a positively charged nucleus at the center and a number of negatively charged electrons outside, the next step was to find the exact size of the nuclear charge and the exact number of electrons for the different varieties of atoms. The answer came through a line of research that began with the English physicist Charles Glover Barkla, 1877 to 1944. In 1911, he noted that when X-rays passed through atoms, some were absorbed and some bounced back. Those that bounced back had a certain ability to penetrate other matter. When the X-rays struck atoms of high atomic weight, the X-rays that bounced back were particularly penetrating. In fact, each different type of atom seemed associated with reflected X-rays of a particular penetrating power. So Barkla called these characteristic X-rays. In 1913, another English physicist, Henry Gwyn Jeffreys Moseley, 1887 to 1915, went into the matter more thoroughly. He measured the exact wavelength of the characteristic X-rays by reflecting them from certain crystals. In crystals, atoms are arranged in regular order and at known distances from each other. X-rays reflecting from, or more accurately, diffracting from, crystals are bent out of their path by the rows of atoms. The longer their waves, the more they are bent. From the degree of bending, the wavelength of the waves can be determined. Moseley found that the greater the atomic weight of an atom, the shorter the waves of the characteristic X-rays associated with it, and the more penetrating those X-rays were. There was such a close connection, in fact, that Moseley could arrange the elements in order according to the wavelength of the characteristic X-rays. For some 40 years prior to this, the elements had been listed in order of atomic weight. This was useful, especially since the Russian chemist Dmitry I. Mendeleev, 1834 to 1907, had arranged them in a periodic table, based on the atomic weight order, in such a way that elements of similar properties were grouped together. The elements in this table were sometimes numbered consecutively, atomic number, but this was inconvenient, since when new elements were discovered, the list of atomic numbers might have to be reorganized. The Danish physicist Niels Bohr, 1885 to 1962, had just advanced a theory of atomic structure that made it reasonable to suppose that the wavelength of the characteristic X-rays depended on the size of the nuclear charge of the atoms making up a particular element. Moseley therefore suggested that these X-rays be used to determine the size of the positive charge on its nucleus. The atomic number could then be set equal to that charge and be made independent of new discoveries of elements. Hydrogen, for instance, has an atomic number of 1. Its nucleus carries a unit positive charge +1, and the hydrogen atom possesses 1 electron to balance this. Helium, with an atomic number of 2, has a nuclear charge of +2 and 2 electrons, with a total charge of -2 to balance it. The alpha particle released by radioactive atoms is identical with a helium nucleus. The atomic number increases as one goes up the line of atoms. Oxygen atoms, for instance, have an atomic number of 8, and iron atoms have one of 26. At the upper end, thorium is 90, and uranium is 92. Each uranium atom has a nucleus bearing a charge of +92, and contains 92 electrons to balance this. Once the notion of the atomic number was worked out, it became possible to tell for certain whether any elements remained as yet undiscovered, and if so, where in the list they might be. Thus, when Moseley first presented scientists with the atomic number, it turned out that there were still 7 elements that were not discovered. At least elements with atomic numbers of 43, 61, 72, 75, 85, 87, and 91 were still not known. By 1945, all 7 had been discovered. It quickly turned out that the atomic number was more fundamental and more characteristic of a particular element than was the atomic weight. Since Dalton's time, it had been assumed that all the atoms of a particular element were of equal atomic weight, and that atoms of 2 different elements were always of different atomic weight. The first inkling and the first proof that this might not be so came through the study of radioactivity. Isotopes. In 1902, Rutherford and his co-worker Frederick Soddy, 1877 to 1956, showed that when uranium atoms gave off alpha particles, a new kind of atom was formed that was not uranium at all. It was this new atom that was eventually found to give off a beta particle, and then another atom of still another element was formed. This work of Rutherford and Soddy began a line of investigation that by 1907 had shown that there was a whole radioactive chain of elements, each one breaking down to the next in line by giving off either an alpha particle or a beta particle, until finally a lead atom was formed that was not radioactive. There was, in short, a radioactive series, beginning with uranium, atomic number 92, and ending with lead, atomic number 82. The same was true of thorium, atomic number 90, which began a series that also ended with lead. Still a third element, actinium, atomic number 89, was at that time the first known member of a series that also ended in lead. The various atoms formed in these three radioactive series were not all different in every way. When the uranium atom gives off an alpha particle, it forms an atom originally called uranium X1. On close examination, it turned out that this uranium X1 had the chemical properties of thorium. Uranium X1 had, however, radioactive properties different from ordinary thorium. Uranium X1 broke down so rapidly, giving off beta particles as it did so, that half of any given quantity would have broken down in 24 days. Another way of saying this, which was introduced by Rutherford, was that the half-life of uranium X1 is 24 days. Ordinary thorium, however, gives off alpha particles, not beta particles, and does so at such a slow rate that its half-life is 14 billion years. Uranium X1 and ordinary thorium were in the same place in the list of elements by chemical standards, and yet there was clearly something different about the two. Here is another case. In 1913, the British chemist Alexander Fleck, born 1889, studied radium B and radium D, the names given to two different kinds of atoms, in the uranium radioactive series. He also studied thorium B in the thorium radioactive series and actinium B in the actinium radioactive series. All four are chemically the same as ordinary lead. All four are in the same place in the list of elements, yet each is different from the radioactive standpoint. Though all give off beta particles, radium B has a half-life of 27 minutes, radium D one of 19 years, thorium B one of 11 hours, and actinium B one of 36 minutes. In 1913, Soddy called atoms that were in the same place in the list of elements, but which had different radioactive properties, isotopes, from Greek words meaning same place. At first, it seemed that the only difference between isotopes might be in their radioactive properties, and that only radioactive atoms were involved. Quickly, that proved not to be so. It proved that it was possible to have several forms of the same element that were all different, even though none of them were radioactive. The uranium series, the thorium series, and the actinium series all ended in lead. In each case, the lead formed was stable, not radioactive. Were the lead atoms identical in every case? Soddy had worked out the way in which atomic weights altered every time an alpha particle or a beta particle was given off by an atom. Working through the three radioactive series, he decided that the lead atoms had different atomic weights in each case. The uranium series ought to end with lead atoms that had an atomic weight of 206. The thorium series ought to end in lead atoms with an atomic weight of 208, and the actinium series in lead atoms with an atomic weight of 207. If this were so, there would be 3 lead isotopes that would differ not in radioactive properties, but in atomic weight. The isotopes could be referred to as lead-206, lead-207, and lead-208. If we use the chemical symbol for lead, Pb, we would write these isotopes superscript 206 Pb, superscript 207 Pb, and superscript 208 Pb. We read the symbol superscript 206 Pb as lead-206. Atomic weight measurements made in 1914 by Soddy and others supported that theory. All 3 lead isotopes had the same atomic number of 82. The atoms of all 3 isotopes had nuclei with an electric charge of plus 82, and all 3 had 82 electrons in the atom to balance that positive nuclear charge. The difference was in the mass of the nucleus only. But what of ordinary lead that existed in the rocks far removed from any radioactive substances, and that had presumably been stable through all the history of Earth? Its atomic weight was 207.2. Was the stable lead that had no connection with radioactivity made up of atoms of still another isotope, one with a fractional atomic weight? Or could stable lead be made up of a mixture of isotopes, each of a different whole number atomic weight? And was the overall atomic weight a fraction only because it was an average? It was at the moment difficult to tell in the case of lead, but an answer came in connection with another element, the rare gas neon, atomic symbol Ne, which has an atomic weight of 20.2. Was that fractional atomic weight something that was possessed by all neon atoms without exception, or was it the average of some lightweight atoms and some heavyweight ones? It would be a matter of crucial importance if isotopes of neon could be found, for neon had nothing to do with any of the radioactive series. If neon had isotopes, then any element might have them. In 1912, Thomson was working on neon. He sent a stream of cathode ray electrons through neon gas. The electrons smashed into the neon atoms and knocked an electron off some of them. That left a neon ion carrying a single positive charge, an ion that could be written Ne+. The neon ions move in the electric field as electrons do, but in the opposite direction since they have an opposite charge. In the combined presence of a magnet and of an electric field, the neon ions move in a curved path. If all the neon ions had the same mass, all would follow the same curve. If some were more massive than others, the more massive ones would curve less. The neon ions ended on a photographic plate, which was darkened at the point of landing. There were 2 regions of darkening, because there were neon ions of 2 different masses that curved in 2 different degrees and ended in 2 different places. Thomson showed from the amount of curving that there was a neon isotope with an atomic weight of 20, and one with an atomic weight of 22.
Neon 20 and Neon 22.
What's more, from the intensity of darkening, it could be seen that ordinary neon was made up of atoms that were roughly 90% neon 20 and 10% neon 22. The overall atomic weight of neon, 20.2, was the average atomic weight of these 2 isotopes. Thomson's instrument was the first one capable of separating isotopes, and such instruments came to be called mass spectrometers. The first to use the name was the English physicist Francis William Aston, 1877 to 1945, who built the first efficient instrument of this type in 1919. He used it to study as many elements as he could. He and those who followed him located many isotopes and determined the frequency of their occurrence with considerable precision. It turned out, for instance, that neon is actually 90.9% neon 20 and 8.8% neon 22. Very small quantities of still a third isotope, neon 21, are also present, making up 0.3%. As for ordinary lead in non-radioactive rocks, it is made up of 23.6% lead-206, 22.6% lead-207, and 52.3% lead-208. There is still a fourth isotope, lead-204, which makes up the remaining 1.5%, and which is not the product of any radioactive series at all. The isotopes always have atomic weights that are close to but not quite whole numbers. Any atomic weight of an element that departs appreciably from an integer does so only because it is an average of different isotopes. For instance, the atomic weight of chlorine, chemical symbol Cl, is 35.5, but this is because it is made up of a mixture of two isotopes. About 1/4 of chlorine's atoms are chlorine 37, and about 3/4 are chlorine 35. To avoid confusion, the average mass of the isotopes that make up a particular element is still called the atomic weight of that element. The integer closest to the mass of the individual isotope is spoken of as the mass number of that isotope. Thus, chlorine is made up of isotopes with mass numbers 35 and 37, but the atomic weight of chlorine as it is found in nature is 35.5, or to be more accurate, 35.453. In the same way, ordinary lead is made up of isotopes with mass numbers 204, 206, 207, and 208, and its atomic weight is 207.19. Neon is made up of isotopes with mass numbers 20, 21, and 22, and its atomic weight is 20.183, and so on. If the atomic weight of some element happens to be very close to a whole number to begin with, it may consist of a single kind of atom. For instance, the gas fluorine, chemical symbol F, has an atomic weight of nearly 19, while that of the metal sodium, chemical symbol Na, is nearly 23. As it turns out, all of the atoms of fluorine are of the single variety, fluorine 19, while all the atoms of sodium are sodium 23. Sometimes the atomic weight of an element as it occurs in nature is nearly a whole number, and yet it is made up of more than one isotope. In that case, one of the isotopes make up very nearly all of it, while the others are present in such minor quantities that the average is hardly affected. Helium, for instance, atomic symbol He, has an atomic weight of just about 4, and indeed almost all the atoms making it up are helium-4. However, 1/1000th of 1% of the atoms, or 1 out of a million, are helium-3. Again, 99.6% of all the nitrogen atoms, atomic symbol N, are nitrogen-14, but 0.4% are nitrogen-15. Then 98.9% of all carbon atoms, atomic symbol C, are carbon-12, but 1.1% are carbon-13. It is not surprising that the atomic weights of nitrogen and carbon are just about 14 and 12, respectively. Even hydrogen does not escape. Its atomic weight is just about 1, and most of its atoms are hydrogen-1. The American chemist Harold Clayton Urey, born 1893, detected the existence of a more massive isotope, hydrogen-2. This isotope has almost twice the mass of the lighter one. No other isotopes of a particular atom differ in mass by so large a factor. For that reason, hydrogen-2 and hydrogen-1 differ in ordinary chemical properties more than isotopes usually do, and Urey therefore gave hydrogen-2 the special name of deuterium, from a Greek word meaning second. In 1929, the American chemist William Francis Giacché, born 1895, found that oxygen was composed of more than one isotope. Its atomic weight had been set arbitrarily at 16 exactly, so it was a relief that 99.76% of its atoms were oxygen-16. However, 0.20% were oxygen-18 and 0.04% were oxygen-17. As you see, oxygen-16 must have a mass number of slightly less than 16.00, and it must be the more massive isotopes, oxygen-17 and oxygen-18, that pull the average up to 16.00. Disregarding this, chemists clung to a standard atomic weight of 16.00 for oxygen as it appeared in nature, preferring not to concern themselves with the separate isotopes. Physicists, however, felt uneasy at using an average as standard, for they were more interested in working with individual isotopes. They preferred to set oxygen-16 at 16.00, so that the average atomic weight of oxygen was 16.0044, and all other atomic weights rose in proportion. Atomic weights determined by this system were physical atomic weights. Finally, in 1961, a compromise was struck. Chemists and physicists alike decided to consider the atomic weight of carbon-12 as exactly 12, and to use that as a standard. By this system, the atomic weight of oxygen became 15.9994, which is only very slightly less than 16. The radioactive elements did not escape this new view either. The atomic weight of uranium, chemical symbol U, is just about 238, and indeed, most of its atoms are uranium-238. In 1935, however, the Canadian-American physicist Arthur Jeffrey Dempster, 1886 to 1950, found that 0.7% of its atoms were a lighter isotope, uranium-235. These differed considerably in radioactive properties. The common uranium isotope, uranium-238, had a half-life of 4,500 million years, while uranium-235 had a half-life of only 700 million years. Furthermore, U-235 broke down in 3 stages to actinium. It was uranium-235, not actinium itself, that was the beginning of the actinium radioactive series. As for thorium, atomic symbol Th, with an atomic weight of 232, it did indeed turn out that in the naturally occurring element virtually all the atoms were thorium-232. End of section 1.
Section number 2 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Blaine Aidan McCoy, Riverside, California, 2019.
Energy. The law of conservation of energy. We have now gone as far as we conveniently can in considering the intertwining strands of the atom and of electricity. It is time to turn to the third strand, energy. To physicists, The concept of work is that of exerting a force on a body and making it move through some distance. To lift a weight against the pull of gravity is work. To drive a nail into wood against the friction of its fibers is work. Anything capable of performing work is said to possess energy, from Greek words meaning work within. There are various forms of energy. Any moving mass possesses energy by virtue of its motion. That is, a moving hammer will drive a nail into wood, while the same hammer held motionlessly against the nail-head will not do so. Heat is a form of energy, since it will expand steam that will force wheels into motion that can then do work. Electricity, magnetism, sound, and light can be made to perform work and are forms of energy. The forms of energy are so many and so various that scientists were eager to find some rule that covered them all and would therefore serve as a unifying bond. It did not seem impossible that such a rule might exist, since one had been found in connection with matter that appeared in even greater variety than energy did. All matter, whatever its form and shape, possessed mass, and in the 1770s the French chemist Antoine Laurent Lavoisier (1743 to 1794) discovered that the quantity of mass was constant. If a system of matter were isolated and made to undergo complicated chemical reactions, everything about it might change, but not its mass. A solid might turn into a gas. A single substance might change into 2 or 3 different substances, but whatever happened, the total mass at the end was exactly the same, as nearly as chemists could tell, as at the beginning. None was either created or destroyed. However, the nature of the matter might change. This was called the law of conservation of mass. Naturally, it would occur to scientists to wonder if a similar law might hold for energy. The answer wasn't easy to get. It wasn't as simple to measure the quantity of energy as it was to measure the quantity of mass. Nor was it as simple to pen up a quantity of energy and keep it from escaping, or from gaining additional quantity from outside, as it was in the case of mass. Beginning in 1840, however, the English physicist James Prescott Joule (1818 to 1889) began a series of experiments in which he made use of every form of energy he could think of. In each case he turned it into heat and allowed the heat to raise the temperature of a given quantity of water. He used the rise in temperature as a measure of the energy. By 1847 he was convinced that any form of energy could be turned into fixed and predictable amounts of heat, that a certain amount of work was equivalent to a certain amount of heat. In that same year, the German physicist Hermann Ludwig Ferdinand von Helmholtz (1821 to 1894) advanced the general notion that a fixed amount of energy in one form was equal to the same amount of energy in any other form. Energy might change its form over and over, but not change its amount. None could either be destroyed or created. This is the law of conservation of energy. Chemical energy. There is energy in a piece of wood. Left quietly to itself, it seems completely incapable of bringing about any kind of work. Set it on fire, however, and the wood plus the oxygen in the air will give off heat and light that are clearly forms of energy. The heat could help boil water and run a steam engine. The amount of energy in burning wood could be measured if it were mixed with air and allowed to burn in a closed container that was immersed in a known quantity of water. From the rise in temperature of the water, the quantity of energy produced could be measured in units called calories, from a Latin word for heat. The instrument was therefore called a calorimeter. In the 1860s, the French chemist Pierre-Eugène Marcellin Berthelot, 1827 to 1907, carried through hundreds of such determinations. His work, and similar work by others, made it clear that such chemical energy, the energy derived from chemical changes in matter, fit the law of conservation of energy. Here's how it looked in the last decades of the 19th century. Molecules are composed of combinations of atoms. Within the molecules, the atoms stick together more or less tightly. It takes a certain amount of energy to pull a molecule apart into separate atoms against the resistance of the forces holding them together. If, after being pulled apart, the atoms are allowed to come together again, they give off energy. The amount of energy they give off in coming together is exactly equal to the amount of energy that they had to gain before they could separate. This is true of all substances. For instance, hydrogen gas, as it is found on Earth, is made up of molecules containing 2 hydrogen atoms each, symbolized as H2. Add a certain amount of energy and you pull the atoms apart. Allow the atoms to come back together into paired molecules, and the added energy is given back again. The same is true for the oxygen molecule, which is made up of 2 oxygen atoms, symbolized as O2, and of the water molecule, symbolized as H2O. Always the amount of energy absorbed in one change is given off in the opposite change. The amount absorbed and the amount given off are always exactly equal. However, the amount of energy involved differs from molecule to molecule. It is quite hard to pull hydrogen molecules apart, and it is even harder to pull oxygen molecules apart. You have to supply about 12% more energy to pull an oxygen molecule apart than to pull a hydrogen molecule apart. Naturally, if you let 2 oxygen atoms come together to form an oxygen molecule, you get back 12% more energy than if you allow 2 hydrogen atoms to come together to form a hydrogen molecule. It takes a considerably larger amount of energy to pull apart a water molecule into separate atoms than to pull apart either hydrogen or oxygen molecules. Naturally, that greater energy is also returned once the hydrogen and oxygen atoms are allowed to come back together into water molecules. Next, imagine pulling apart hydrogen and oxygen molecules into hydrogen and oxygen atoms, and then having those atoms come together to form water molecules. A certain amount of energy is put into the system to break up the hydrogen and oxygen molecules, but then a much greater amount of energy is given off when the water molecules form. It is for that reason that a great deal of energy, mostly in the form of heat, is given off if a jet of hydrogen gas and a jet of oxygen gas are allowed to mix in such a way as to form water. Just mixing the hydrogen and oxygen is not enough. The molecules of hydrogen and oxygen must be separated, and that takes a little energy. The energy in a match flame is enough to raise the temperature of the mixture and make the hydrogen and oxygen molecules move about more rapidly and more energetically. This increases the chance that some molecules will be broken up into separate atoms, though the actual process is rather complicated. An oxygen atom might then strike a hydrogen molecule to form water, and more energy is given off than was absorbed from the match flame. The temperature goes up still higher, so that further breakup among the oxygen and hydrogen molecules is encouraged. This happens over and over again, so that in a very little time the temperature is very high, and the hydrogen and oxygen are combining to form water at an enormous rate. If a great deal of hydrogen and oxygen are well mixed to begin with. The rate of reaction is so great that an explosion occurs. Such a situation in which each reacting bit of the system adds energy to the system by its reaction and brings about more reactions like itself is called a chain reaction. Thus, a match flame put to one corner of a large sheet of paper will set that corner burning. The heat of the burning will ignite a neighboring portion of the sheet, and so on till the entire sheet is burned. For that matter, a single smoldering cigarette end can serve to burn down an entire forest in a vastly destructive chain reaction. Electrons and energy. The discovery of the structure of the atom sharpened the understanding of chemical energy. In 1904, the German chemist Richard Abegg, 1869 to 1910, first suggested that atoms were held together through the transfer of electrons from one atom to another. To see how this worked, one began by noting that electrons in an atom existed in a series of shells. The innermost shell could hold only 2 electrons. The next shell could hold 8, the next 18, and so on. It turned out that some electron arrangements were more stable than others. If only the innermost shell contained electrons, and it were filled with the 2 electrons that were all it could hold, then that was a stable arrangement. If an atom contained electrons in more than one shell, and the outermost shell that held electrons held 8, that was a stable arrangement too. Thus the helium atom has 2 electrons only, filling the innermost shell, and that is so stable an arrangement that helium undergoes no chemical reactions at all. The neon atom has 10 electrons, 2 in the innermost shell and 8 in the next electron shell, and it does not react. The argon atom has 18 electrons, 2, 8, and 8, and it too is very stable. But what if an atom did not have its electron shell so neatly filled? The sodium atom has 11 electrons, 2, 8, and 1, while the fluorine atom has 9 electrons, 2 and 7. If the sodium atom passed one of its electrons to a fluorine atom, both would have the stable configuration of neon, 2 and 8. This, therefore, ought to have a great tendency to happen. If it did happen, though, the sodium atom minus 1 electron would have a unit positive charge and would be sodium plus, a positively charged ion. Fluorine with 1 electron in excess would become fluorine minus, a negatively charged ion. The 2 ions with opposite charges would cling together, since opposite charges attract, and thus the molecule of sodium fluoride would be formed. In 1916, the American chemist Gilbert Newton Lewis, 1875 to 1946, carried this notion farther. Atoms could cling together not only as a result of the outright transfer of 1 or more electrons, but through sharing pairs of electrons. This sharing could only take place if the atoms remained close neighbors, and it would take energy to pull them apart and break up the shared pool, just as it would take energy to pull 2 ions apart against the attraction of opposite charges. In this way, the vague notions of atoms clinging together in molecules and being forced apart gave way to a much more precise picture of electrons being transferred or shared. The electron shifts
Could be dealt with mathematically
by a system that came to be called quantum mechanics, and chemistry was thus made a more exact science than it had ever been before. The energy of the sun. The most serious problem raised by the law of conservation of energy involved the sun. Until 1847, scientists did not question sunlight. The sun radiated vast quantities of energy, but that apparently was its nature, and was no more to be puzzled over than the fact that the earth rotated on its axis. Once Helmholtz had stated that energy could neither be created nor destroyed, however, he was bound to ask where the sun's energy came from. It had, to man's best knowledge, been radiating heat and light with no perceptible change throughout the history of civilization, and, from what biologists and geologists could deduce, for countless ages earlier. Where then did that energy come from? The sun gave the appearance of being a huge globe of fire. Could it actually be that? A large heap of burning fuel, turning chemical energy into heat and light? The sun's mass was known, and its rate of energy production was known. Suppose the sun's mass were a mixture of hydrogen and oxygen, and it were burning at a rate sufficient to produce the energy at the rate it was giving it off. If that were so, all the hydrogen and oxygen in its mass would be consumed in 1,500 years. No chemical reaction in the sun could account for its having given us heat and light since the days of the pyramids, let alone since the days of the dinosaurs. Was there some source of energy greater than chemical energy? What about the energy of motion? Helmholtz suggested that meteors might be falling into the sun at a steady rate. The energy of their collisions might then be converted into heat and light, and this could keep the sun shining for as long as the supply of meteors held out, even millions of years. This, however, would mean that the sun's mass would be increasing steadily, and so would the force of its gravitational pull. With the sun's gravitational field increasing steadily, the length of Earth's year would be decreasing at a measurable rate. But it wasn't. In 1854, Helmholtz came up with something better. He suggested that the sun was contracting. Its outermost layers were falling inward, and the energy of this fall was converted into heat and light. What's more, this energy would be obtained without any change in the mass of the sun whatsoever. Helmholtz calculated that the sun's contraction over the 6,000 years of recorded history would have reduced its diameter only 560 miles, a change that would not have been noticeable to the unaided eye. Since the development of the telescope 2.5 centuries earlier, the decrease in diameter would have only been 23 miles, and that was not measurable by the best techniques of Helmholtz's day. Working backward, however, it seemed that 25 million years ago, the sun must have been so large as to fill the Earth's orbit. Clearly, the Earth could not then have existed. In that case, the maximum age of the Earth was only 25 million years. Geologists and biologists found themselves disturbed by this. The slow changes in the Earth's crust and in the evolution of life made it seem very likely that the Earth must have been in existence, with the sun delivering heat and light very much in the present fashion, for many hundreds of millions of years. Yet there seemed absolutely no other way of accounting for the sun's energy supply. Either the law of conservation of energy was wrong, which seemed unlikely, or the painfully collected evidence of geologists and biologists was wrong, which seemed unlikely, or there was some source of energy greater than any known in the 19th century, whose existence had somehow escaped mankind, which also seemed unlikely. Yet one of those unlikely alternatives would have to be true. Then, in 1896, came the discovery of radioactivity. The energy of radioactivity. It eventually became clear that radioactivity involved the giving off of energy. Uranium emitted gamma rays that we now know to be 100,000 times as energetic as ordinary light rays. What's more, alpha particles were being emitted at velocities of perhaps 30,000 kilometers per second. while the lighter beta particles were being shot off at velocities of up to 250,000 kilometers per second, about 0.8 times the velocity of light. At first, the total energy given off by radioactive substances seemed so small that there was no use worrying about it. The amount of energy liberated by a gram of uranium in 1 second of radioactivity was an insignificant fraction of the energy released by a burning candle. In a few years, however, something became apparent. A lump of uranium might give off very little energy in a second, but it kept on for second after second, day after day, month after month, and year after year with no perceptible decrease. The energy released by the uranium over a very long time grew to be enormous. It eventually turned out that while the rate at which uranium delivered energy did decline, it did so with such unbelievable slowness that it took 4.5 billion years for that rate to decrease to half of what it was to begin with. If all the energy delivered by a gram of uranium in the course of its radioactivity over many billions of years was totaled, it was enormously greater than the energy produced by the burning of a candle with a mass equal to that of uranium. Let's put it another way. We might think of a single uranium atom breaking down and shooting off an alpha particle. We might also think of a single carbon atom combining with 2 oxygen atoms to form carbon dioxide. The uranium atom would give off 2 million times as much energy in breaking down as the carbon atom would in combining. The energy of radioactivity is millions of times as intense as the energy released by chemical reactions. The reason mankind had remained unaware of radioactivity and very aware of chemical reactions was, first, that the most common radioactive processes are so slow that their great energies were stretched over such enormous blocks of time as to be insignificant on a per-second basis. Secondly, chemical reactions are easily controlled by changing quantities, concentrations, temperatures, pressures, states of mixture, and so on, and this makes them easy to take note of and to study. The rate of radioactive changes, however, could not apparently be altered. The early investigators quickly found that the breakdown of uranium-238, for instance, could not be hastened by heat, pressure, changes in chemical combination, or indeed anything else they could think of. It remained incredibly slow. But despite all this, radioactivity had at last been discovered, and the intensity of its energies was recognized and pointed out in 1902 by Marie Curie and her husband Pierre Curie, 1859 to 1906. Where then did the energy come from? Could it come from the outside? Could the radioactive atoms somehow collect energy from their surroundings, concentrate it several millionfold, and then let it out all at once? To concentrate energy in this fashion would violate something called the second law of thermodynamics. This was first proposed in 1850 by the German physicist Rudolf Julius Emanuel Clausius, 1822 to 1828, and had proved so useful that physicists did not like to abandon it unless they absolutely had to. Another possibility was that radioactive atoms were creating energy out of nothing. This, of course, violated the law of conservation of energy, also called the first law of thermodynamics, and physicists preferred not to do that either. The only thing that seemed to remain was to suppose that somewhere within the atom was a source of energy that had never made itself evident to humanity until the discovery of radioactivity. Becquerel was one of the first to suggest this. It might have seemed at first that only radioactive elements had this supply of energy somewhere within the atom. But in 1903, Rutherford suggested that all atoms had a vast energy supply hidden within themselves. The supply in uranium and thorium leaked slightly, so to speak, and that was all that made them different. But if a vast supply of energy existed in atoms, it was possible that the solution to the puzzle of the sun's energy might rest there. As early as 1899, the American geologist Thomas Trouder Chamberlain, 1843 to 1928, was already speculating about a possible connection between radioactivity and the sun's energy. If it were some variety of this newly discovered source of energy, not necessarily ordinary radioactivity, of course, that powered the sun, millions of times as intense as chemical energy, then the sun might be pouring out energy for hundreds of millions of years without perceptible physical change, just as uranium would show scarcely any change, even in so mighty a time span. The sun would not have to be contracting. It would not have had to fill the Earth's orbit 25 million years ago. This was all exciting, but in 1900, the structure of the atom had not yet been worked out, and this new energy was just a vague supposition. No one had any idea of what it actually might be, or where in the atom it might be located. It could only be spoken of as existing within the atom, and therefore was called atomic energy. Through long habit, it is still called that much of the time, and yet atomic energy is not a good name. In the first couple of decades of the 20th century, it became apparent that ordinary chemical energy involved electron shifts, and those electrons were certainly components of atoms. This meant that a wood fire was a kind of atomic energy. The electrons, however, existed only in the outer regions of the atom. Once Rutherford worked out the theory of the nuclear atom, it became apparent that the energy involved in radioactivity and in solar radiation had to involve components of the atom that were more massive and more energetic than the light electrons. The energy had to come somehow from the atomic nucleus. What is involved, then, in radioactivity and in the sun is nuclear energy. That is the proper name for it. And in the next section, we will consider the subsequent history of the nuclear energy that broke upon the startled consciousness of scientists as the 20th century opened, and which, less than half a century later, was to face mankind with untold consequences for good and for evil.
End of Section 2. Recording by Blaine Aidan McCoy, Riverside, California. Section 3. Worlds Within Worlds, the Story of Nuclear Energy. Mass and Energy. In 1900, it began to dawn on physicists that there was a vast store of energy within the atom, a store no one earlier had imagined existed. The sheer size of the energy store in the atom, millions of times that known to exist in the form of chemical energy, seemed unbelievable at first. Yet that size quickly came to make sense as a result of a line of research that seemed, at the beginning, to have nothing to do with energy. Suppose a ball were thrown forward at a velocity of 20 kilometers per hour by a man on top of a flat car that is moving forward at 20 kilometers an hour. To someone watching from the roadside, the ball would appear to be traveling at 40 kilometers an hour. The velocity of the thrower is added to the velocity of the ball. If the ball were thrown forward at 20 kilometers an hour by a man on top of a flat car that is moving backward at 20 kilometers an hour, then the ball, to someone watching from the roadside, would seem to be not moving at all after it left the hand of the thrower, it would just drop to the ground. There seemed no reason in the 19th century to suppose that light didn't behave in the same fashion. It was known to travel at the enormous speed of just a trifle under 300,000 kilometers per second, while Earth moved in its orbit about the Sun at a speed of about 30 kilometers per second. Surely, if a beam of light beginning at some earthbound source shone in the direction of Earth's travel, it ought to move at a speed of 300,030 kilometers per second. If it shone in the opposite direction, against Earth's motion, it ought to move at a speed of 299,970 kilometers per second. Could such a small difference in an enormous speed be detected? The German-American physicist Albert Abraham Michelson, 1852 to 1931, had invented a delicate instrument, the interferometer, that could compare the velocities of different beams of light with great precision. In 1887, he and a co-worker, the American chemist Edward Williams Morley, 1838 to 1923, tried to measure the comparative speeds of light using beams headed in different directions. Some of this work was performed at the U.S. Naval Academy and some at the Case Institute. The results of the Michelson-Morley experiment were unexpected. It showed no difference in the measured speed of light, no matter what the direction of the beam, whether it went in the direction of the Earth's movement, or against it, or at any angle to it. The speed of light always appeared to be exactly the same. To explain this, the German-Swiss-American scientist Albert Einstein, 1879 to 1955, advanced his special theory of relativity in 1905. According to Einstein's view, speeds could not merely be added. A ball thrown forward at 20 kilometers an hour by a man moving at 20 kilometers an hour in the same direction would not seem to be going 40 kilometers an hour to an observer at the roadside. It would seem to be going very slightly less than 40 kilometers an hour, so slightly less that the difference couldn't be measured. However, as speeds grew higher and higher, the discrepancy in the addition grew greater and greater, according to a formula Einstein derived, until, at velocities of tens of thousands of kilometers per hour, that discrepancy could be easily measured. At the speed of light, which Einstein showed was a limiting velocity that an observer could never reach, the discrepancy became so great that the speed of the light source, however great, added or subtracted 0 to or from the speed of light. Accompanying this were all sorts of other effects. It could be shown by Einstein's reasoning that no object possessing mass could move faster than the speed of light. What's more, as an object moved faster and faster, its length in the direction of motion, as measured by a stationary observer, grew shorter and shorter, while its mass grew greater and greater. At 260,000 kilometers per second, its length in the direction of movement was only half what it was at rest, and its mass was twice what it was. As the speed of light was approached, its length would approach 0 in the direction of motion, while its mass would approach the infinite. Could this really be so? Ordinary objects never moved so fast as to make their lengths and masses show any measurable change. What about subatomic particles, however, which moved at tens of thousands of kilometers per second? The German physicist Alfred Heinrich Bucherer, 1863 to 1927, reported in 1908 that speeding electrons did gain in mass, just the amount predicted by Einstein's theory. The increased mass with energy has been confirmed with great precision in recent years. Einstein's special theory of relativity has met many experimental tests exactly ever since, and it is generally accepted by physicists today. Einstein's theory gave rise to something else as well. Einstein deduced that mass was a form of energy. He worked out a relationship, the mass-energy equivalence, that is expressed as follows: E equals mc squared, where E represents energy, m is mass, and c is the speed of light. If mass is measured in grams and the speed of light is measured in centimeters per second, then the equation will yield the energy in a unit called ergs. It turns out that 1 gram of mass is equal to 900 billion ergs of energy. The erg is a very small unit of energy, but 900 billion of them mount up. The energy equivalent of 1 gram of mass, and remember that a gram in ordinary units is only 1/28th of an ounce, would keep a 100-watt light bulb burning for 35,000 years. It is this vast difference between the tiny quantity of mass and the huge amount of energy to which it is equivalent that obscured the relationship over the years. When a chemical reaction liberates energy, the mass of the materials undergoing the reaction decreases slightly, but very slightly. Suppose, for instance, a gallon of gasoline is burned. The gallon of gasoline has a mass of 2,800 grams and combines with about 10,000 grams of oxygen to form carbon dioxide and water, yielding 1.35 billion ergs. That's a lot of energy, and it will drive an automobile for some 25 to 30 kilometers. But by Einstein's equation, all that energy is equivalent to only a little over a millionth of a gram. You start with 12,800 grams of reacting material, and you end up with 12,800 grams minus a millionth of a gram or so that was given off as energy. No instruments known to the chemists of the 19th century could have detected so tiny a loss of mass in such a large total. No wonder, then, that from Lavoisier on, scientists thought that the law of conservation of mass held exactly. Radioactive changes gave off much more energy per atom than chemical changes did, and the percentage loss in mass was correspondingly greater. The loss of mass in radioactive changes was found to match the production of energy in just the way Einstein predicted. It was no longer quite accurate to talk about the conservation of mass after 1905, even though mass was just about conserved in ordinary chemical reactions, so that the law could continue to be used by chemists without trouble. Instead, it is more proper to speak of the conservation of energy and to remember that mass was one form of energy and a very concentrated form. The mass-energy equivalence fully explained why the atom should contain so great a store of energy. Indeed, the surprise was that radioactive changes gave off as little energy as they did. When a uranium atom broke down through a series of steps to a lead atom, it produced 1,000,000 times as much energy as that same atom would release if it were involved in even the most violent of chemical changes. Nevertheless, that enormous energy change in the radioactive breakdown represented only about 0.5% of the total energy to which the mass of the uranium atom was equivalent. Once Rutherford worked out the nuclear theory of the atom, it became clear from the mass-energy equivalence that the source of the energy of radioactivity was likely to be in the atomic nucleus, where almost all of the mass of the atom was to be found. The attention of physicists, therefore, turned to the nucleus. The structure of the nucleus. The proton. As early as 1886, Eugene Goldstein, who was working with cathode rays, also studied rays that moved in the opposite direction. Since the cathode rays, electrons, were negatively charged, rays moving in the opposite direction would have to be positively charged. In 1907, J.J. Thomson called them positive rays. Once Rutherford worked out the nuclear structure of the atom, it seemed clear that the positive rays were atomic nuclei from which a number of electrons had been knocked away. These nuclei came in different sizes. Were the nuclei single particles, a different one for every isotope of every element, or were they all built up out of numbers of still smaller particles of a very limited number of varieties? Might it be that the nuclei owed their positive electrical charge to the fact that they contained particles just like the electron, but ones that carried a positive charge rather than a negative one? All attempts to discover this positive electron in the nuclei failed, however. The smallest nucleus found was that produced by knocking the single electron off a hydrogen atom in one way or another. This hydrogen nucleus had a single positive charge, one that was exactly equal in size to the negative charge on the electron. The hydrogen nucleus, however, was much more massive than an electron. The hydrogen nucleus with its single positive charge was approximately 1,837 times as massive as the electron with its single negative charge. Was it possible to knock the positive charge loose from the mass of the hydrogen nucleus? Nothing physicists did could manage to do that. In 1914, Rutherford decided the attempt should be given up. He suggested that the hydrogen nucleus, for all its high mass, should be considered the unit of positive electrical charge, just as the electron was the unit of negative electrical charge. He called the hydrogen nucleus a proton, from the Greek word for first, because it was the nucleus of the first element. Why the proton should be so much more massive than the electron is still one of the unanswered mysteries of physics. The proton-electron theory. What about the nuclei of elements other than hydrogen? All the other elements had nuclei more massive than that of hydrogen, and the natural first guess was that these were made up of some appropriate number of protons closely packed together. The helium nucleus, which had a mass 4 times as great as that of hydrogen, might be made up of 4 protons. The oxygen nucleus, with a mass number of 16, might be made up of 16 protons, and so on. This guess, however, ran into immediate difficulties. A helium nucleus might have a mass number of 4, but it had an electric charge of +2. If it were made up of 4 protons, it ought to have an electric charge of +4. In the same way, an oxygen nucleus made up of 16 protons ought to have a charge of +16, but in actual fact it had one of +8. Could it be that something was canceling part of the positive electric charge? The only thing that could do so would be a negative electric charge, and these were to be found only on electrons, as far as anyone knew, in 1914. It seemed reasonable then to suppose that a nucleus would contain about half as many electrons in addition to the protons. The electrons were so light they wouldn't affect the mass much, and they would succeed in canceling some of the positive charge. Thus, according to this early theory, now known to be incorrect, the helium nucleus contained not only 4 protons, but 2 electrons in addition. The helium nucleus would then have a mass number of 4 and an electric charge, atomic number, of 4 minus 2, or 2. This was in accordance with observation. This proton-electron theory of nuclear structure accounted for isotopes very nicely. While oxygen-16 had a nucleus made up of 16 protons and 8 electrons, oxygen-17 had one of 17 protons and 9 electrons, and oxygen-18 had one of 18 protons and 10 electrons. The mass numbers were 16, 17, and 18 respectively, but the atomic number was 16 minus 8, 17 minus 9, and 18 minus 10, or 8 in each case. Again, uranium-238 has a nucleus built up, according to this theory, of 238 protons and 146 electrons, while uranium-235 has one built up of 235 protons and 143 electrons. In these cases, the atomic number is, respectively, 238 minus 146 and 235 minus 143, or 92 in each case. The nucleus of the two isotopes is, however, of different structure, and it is not surprising, therefore, that the radioactive properties of the two, properties that involve the nucleus, should be different, and that the half-life of uranium-238 should be 6 times as long as that of uranium-235. The presence of electrons in the nucleus not only explained the existence of isotopes, but seemed justified by 2 further considerations. First, it is well known that similar charges repel each other, and that the repulsion is stronger the closer together the similar charges are forced. Dozens of positively charged particles squeezed into the tiny volume of an atomic nucleus couldn't possibly remain together for more than a tiny fraction of a second. Electrical repulsion would send them flying apart at once. On the other hand, opposite charges attract, and a proton and an electron would attract each other as strongly as 2 protons or 2 electrons would repel each other. It was thought possible that the presence of electrons in a collection of protons might somehow limit the repulsive force and stabilize the nucleus. Second, there are radioactive decays in which beta particles are sent flying out of the atom. From the energy involved, they could come only out of the nucleus. Since beta particles are electrons, and since they come from the nucleus, it seemed to follow that there must be electrons within the nucleus to begin with. The proton-electron theory of nuclear structure also seemed to account neatly for many of the facts of radioactivity. Why radioactivity at all, for instance? The more complex a nucleus is, the more protons must be squeezed together, and the harder it would seem it must be to keep them together. More and more electrons seemed to be required. Finally, when the total number of protons was 84 or more, no amount of electrons seemed sufficient to stabilize the nucleus. The manner of breakup fits the theory too. Suppose a nucleus gives off an alpha particle. The alpha particle is a helium nucleus made up by this theory of 4 protons and 2 electrons. If a nucleus loses an alpha particle, its mass number should decline by 4 and its atomic number by 4, minus 2, or 2. And indeed, when uranium-238, atomic number 92, gives off an alpha particle, it becomes thorium-234, atomic number 90. Suppose a beta particle is emitted. A beta particle is an electron, and if a nucleus loses an electron, its mass number is almost unchanged. An electron is so light that in comparison with the nucleus, we can ignore its mass. On the other hand, a unit negative charge is gone. One of the protons in the nucleus, which had previously been masked by an electron, is now unmasked. Its positive charge is added to the rest, and the atomic number goes up by 1. Thus, thorium-234, atomic number 90, gives up a beta particle and becomes proactinium-234, atomic number 91. If a gamma ray is given off, that gamma ray has no charge and the equivalent of very little mass. That means that neither the mass number nor the atomic number of the nucleus is changed, although its energy content is altered. Even more elaborate changes can be taken into account. In the long run, uranium-238, having gone through many changes, becomes lead-206. Those changes include the emission of 8 alpha particles and 6 beta particles. The 8 alpha particles involve a loss of 8 times 4, or 32 in mass number, while the 6 beta particles contribute nothing in this respect. And indeed, the mass number of uranium-238 declines by 32 in reaching lead-206. On the other hand, the 8 alpha particles involve a decrease in atomic number of 8 by 2, or 16, while the 6 beta particles involve an increase in atomic number of 6 by 1, or 6. The total change is a decrease of 16 minus 6, or 10, and indeed, uranium atomic number 92 changes to lead atomic number 82. It is useful to go into such detail concerning the proton-electron theory of nuclear structure and to describe how attractive it seemed. The theory appeared solid and unshakable, and indeed physicists used it with considerable satisfaction for 15 years. And yet, as we shall see, it was wrong, and that should point a moral. Even the best-seeming of theories may be wrong in some details and require an overhaul. Protons in nuclei. Let us, nevertheless, go on to describe some of the progress made in the 1920s in terms of the proton-electron theory that was then accepted. Since a nucleus is made up of a whole number of protons, its mass ought to be a whole number if the mass of a single proton is considered 1. The presence of electrons would add some mass, but in order to simplify matters, let us ignore that. When isotopes were first discovered, this indeed seemed to be so. However, Aston and his mass spectrometer kept measuring the mass of different nuclei more and more closely during the 1920s and found that they differed very slightly from whole numbers. Yet, a number of protons turned out to have different masses if they were first considered separately and then as part of a nucleus. Using modern standards, the mass of a proton is 1.007825. 12 separate protons would have a total mass of 12 times that, or 12.0939. On the other hand, if the 12 protons are packed together into a carbon-12 nucleus, the mass is 12. So that the mass of the individual protons is 1.00000 apiece. What happens to this difference of 0.007825 between the proton in isolation and the proton as part of a carbon-12 nucleus? According to Einstein's special theory of relativity, the missing mass would have to appear in the form of energy. If 12 hydrogen nuclei, protons, plus 6 electrons are packed together to form a carbon nucleus, a considerable quantity of energy would have to be given off. In general, Aston found that as one went on to more and more complicated nuclei, a larger fraction of the mass would have to appear as energy, although not in a perfectly regular way, until it reached a maximum in the neighborhood of iron. Iron 56, the most common of the iron isotopes, has a mass number of 55.9349. Each of its 56 protons, therefore, has a mass of 0.9988. For nuclei more complicated than those of iron, the protons in the nucleus begin to grow more massive again. Uranium-238 nuclei, for instance, have a mass of 238.0506, so that each of the 238 protons they contain has a mass of 1.0002. By 1927, Aston had made it clear that it is the middle elements in the neighborhood of iron that are most closely and economically packed. If a very massive nucleus is broken up into somewhat lighter nuclei, the proton packing would be tighter, and some mass would be converted into energy. Similarly, if very light nuclei were joined together into somewhat more massive nuclei, some mass would be converted into energy. This demonstration that energy was released in any shift away from either extreme of the list of atoms according to atomic number fits the case of radioactivity, where very massive nuclei break down into somewhat less massive ones. Consider that uranium-238 gives up 8 alpha particles and 6 beta particles to become lead-206. The uranium-238 nucleus has a mass of 238.0506. Each alpha particle has one of 4.0026 for a total of 32.0208. Each beta particle has a mass of 0.00154 for a total of 0.00924, and the lead-206 nucleus has one of 205.9745. This means that the uranium-238 nucleus, mass 238.0506, changes into 8 alpha particles, 6 beta particles, and a lead-206 nucleus, total mass 238.0045. The starting mass is 0.0461 greater than the final mass, and it is this missing mass that has been converted into energy and is responsible for the gamma rays and for the velocity with which alpha particles and beta particles are discharged. Nuclear bombardment. Once scientists realized that there was energy which became available when one kind of nucleus was changed into another, an important question arose as to whether such a change could be brought about and regulated by man, and whether this might not be made the source of useful power of a kind and amount undreamed of earlier. Chemical energy was easy to initiate and control, since that involved the shifts of electrons on the outskirts of the atoms. Raising the temperature of a system, for instance, caused atoms to move more quickly and smash against each other harder, and that in itself was sufficient to force electrons to shift and to initiate a chemical reaction that would not take place at lower temperatures. To shift the protons within the nucleus, nuclear reactions, and make nuclear energy available was a harder problem by far. The particles involved were much more massive than electrons and correspondingly harder to move. What's more, they were buried deep within the atom. No temperatures available to the physicists of the 1920s could force atoms to smash together hard enough to reach and shake the nucleus. In fact, the only objects that were known to reach the nucleus were speeding subatomic particles. As early as 1906, for instance, Rutherford had used the speeding alpha particles given off by a radioactive substance to bombard matter and to show that sometimes these alpha particles were deflected by atomic nuclei. It was, in fact, by such an experiment that he first demonstrated the existence of such nuclei. Rutherford had continued his experiments with bombardment. An alpha particle striking a nucleus would knock it free of the atom to which it belonged and send it shooting forward like one billiard ball hitting another. The nucleus that shot ahead would strike a film of chemical that scintillated, sparkled, under the impact. In a rough way, one could tell the kind of nucleus that struck from the nature of the sparkling. In 1919, Rutherford bombarded nitrogen gas with alpha particles and found that he obtained the kind of sparkling he associated with the bombardment of hydrogen gas. When he bombarded hydrogen, the alpha particles struck hydrogen nuclei, protons, and shot them forward. To get hydrogen sparkling out of the bombardment of nitrogen, Rutherford felt he must have knocked protons out of the nitrogen nuclei. Indeed, as was later found, he had converted nitrogen nuclei into oxygen nuclei. This was the first time in history that the atomic nucleus was altered by deliberate human act. Rutherford continued his experiments and by 1924 had shown that alpha particles could be used to knock protons out of the nuclei of almost all elements up to potassium, atomic number 19. There were, however, limitations to the use of natural alpha particles as the bombarding agent. First, the alpha particles used in bombardment were positively charged, and so were the atomic nuclei. This meant that the alpha particles and the atomic nuclei repelled each other, and much of the energy of the alpha particle was used in overcoming the repulsion. For more and more massive nuclei, the positive charge grew higher and the repulsion stronger, until for elements beyond potassium, no collision could be forced, even with the most energetic naturally occurring alpha particles. Second, the alpha particles that are sprayed toward the target cannot be aimed directly at the nuclei. An alpha particle strikes a nucleus only if, by chance, they come together. The nuclei that serve as their targets are so unimaginably small that most of the bombarding particles are sure to miss. In Rutherford's first bombardment of nitrogen, it was calculated that only one alpha particle out of 300,000 managed to strike a nitrogen nucleus. The result of these considerations is clear. There is energy to be gained out of nuclear reactions, but there is also energy that must be expended to cause these nuclear reactions. In the case of nuclear bombardment by subatomic particles, the only way, apparently, in which nuclear reactions can be brought about, the energy expended seems to be many times the energy to be extracted. This is because so many subatomic particles use up their energy in ionizing atoms, knocking electrons away, and never initiate nuclear reactions at all. It was as though the only way you could light a candle would be to strike 300,000 matches, one after the other. If that were so, candles would be impractical. In fact, the most dramatic result of alpha particle bombardment had nothing to do with energy production, but rather the reverse. New nuclei were produced that had more energy than the starting nuclei, so that energy was absorbed by the nuclear reaction rather than given off. This first came about in 1934 when a French husband and wife team of physicists, Frédéric Joliot-Curie, 1900 to 1958, and Irene Joliot-Curie, 1897 to 1956, were bombarding aluminum-27, atomic number 13, with alpha particles. The result was to combine part of the alpha particle with the aluminum-27 nucleus to form a new nucleus with an atomic number 2 units higher, 15, and a mass number 3 units higher, 30. The element with atomic number 15 is phosphorus, so that phosphorus 30 was formed. The only isotope of phosphorus that occurs in nature, however, is phosphorus 31. Phosphorus 30 was the first man-made nucleus, the first to be manufactured by nuclear reactions in the laboratory. The reason phosphorus 30 did not occur in nature was that its energy content was too high to allow it to be stable. its energy content drained away through the emission of particles that allowed the nucleus to change over into a stable one, silicon-30, atomic number 14. This was an example of artificial radioactivity. Since 1934, over 1,000 kinds of nuclei that did not occur in nature have been formed in the laboratory through various kinds of bombardment-induced nuclear reactions. Every single one of them proved to be radioactive. Particle accelerators. Was there nothing that could be done to make nuclear bombardment more efficient and increase the chance of obtaining useful energy out of nuclear reactions? In 1928, the Russian-American physicist George Gamow, 1904 to 1968, suggested that protons might be used as bombarding agents in place of alpha particles. Protons were only 1/4 as massive as alpha particles, and the collision might be correspondingly less effective. On the other hand, protons had only half the positive charge of alpha particles and would not be as strongly repelled by the nuclei. Then, too, protons were much more easily available than alpha particles. To get a supply of protons, one only had to ionize the very common hydrogen atoms, i.e., get rid of the single electron of the hydrogen atom, and a single proton is left. Of course, protons obtained by the ionization of hydrogen atoms have very little energy, but could energy be imparted to them? Protons carry a positive charge, and a force can therefore be exerted upon them by an electric or magnetic field. In a device that makes use of such fields, protons can be accelerated, made to go faster and faster, and thus gain more and more energy. In the end, if enough energy is gained, the proton could do more damage than the alpha particle, despite the former's smaller mass. Combine that with the smaller repulsion involved and the greater ease of obtaining protons, and the weight of convenience and usefulness would swing far in the direction of the proton. Physicists began to try to design particle accelerators, and the first practical device of this sort was produced in 1929 by the two British physicists John Douglas Cockcroft, 1897 to 1967, and Ernest Thomas Sinton Walton, born 1903. Their device, called an electrostatic accelerator, produced protons that were sufficiently energetic to initiate nuclear reactions. In 1931, they used their accelerated protons to disrupt the nucleus of lithium-7. It was the first nuclear reaction to be brought about by man-made bombarding particles. Other types of particle accelerators were also being developed at this time. The most famous was the one built in 1930 by the American physicist Ernest Orlando Lawrence, 1901 to 1958. In this device, a magnet was used to make the protons move in gradually expanding circles, gaining energy with each lap until they finally moved out beyond the influence of the magnet and then hurtled out of the instrument in a straight line at maximum energy. This instrument was called a cyclotron. The cyclotron was rapidly improved using larger magnets and increasingly sophisticated design. There are now, at this time of writing, proton synchrotrons, descendants of that first cyclotron, that produce particles with over 1 million times the energy of those produced by Lawrence's first cyclotron. Of course, the first cyclotron was only 1/4 meter wide, while the largest today has a diameter of some 2,000 meters. As particle accelerators grew larger, more efficient, and more powerful, they became ever more useful in studying the structure of the nucleus and the nature of the subatomic particles themselves.
They did not serve, however, to bring the dream of useful nuclear energy any closer. Though they brought about the liberation of vastly more nuclear energy than Rutherford's initial bombardments could, they also consumed a great deal more energy in the process. It is not surprising that Rutherford, the pioneer in nuclear bombardment, was pessimistic. To the end of his days, he died in 1937, he maintained that it would be forever impossible to tap the energy of the nucleus for use by man. Hopes that nuclear power might someday run the world's industries were, in his view, an idle dream. End of Section 3. Section 4 of Worlds Within Worlds. The Story of Nuclear Energy by Isaac Asimov. The neutron, nuclear spin. What Rutherford did not and could not take into account were the consequences of a completely new type of nuclear bombardment involving a type of particle unknown in the 1920s, though Rutherford speculated about the possibility of its existence. The beginnings of the new path came about through the reluctant realization that there was a flaw in the apparently firmly grounded proton-electron picture of nuclear structure. The flaw involved the nuclear spin. In 1924, the Austrian physicist Wolfgang Pauli, 1900 to 1958, worked out a theory that treated protons and electrons as though they were spinning on their axes. This spin could be in either direction, or, as we would say in earthly terms, from west to east or from east to west. Quantum theory has shown that a natural unit exists for what is called the angular momentum of this spin. Measured in terms of this natural unit of spin, the proton and electron have spin 1/2. If the particle spun in one direction, it was plus 1/2. If in the other, it was minus 1/2. When subatomic particles came together to form an atomic nucleus, each kept its original spin, and the nuclear spin was then equal to the total angular momentum of the individual particles that made it up. For instance, suppose the helium nucleus is made up of 4 protons and 2 electrons, as was thought in the 1920s. Of the 4 protons, suppose that 2 had a spin of plus 1/2 and 2 of minus 1/2. Suppose also that of the 2 electrons, 1 had a spin of plus 1/2 and 1 of minus 1/2. All the spins would cancel each other. The total angular momentum would be 0. Of course, it is also possible that all 6 particles were spinning in the same direction, all plus 1/2 or all minus 1/2. In that case, the nuclear spin would be 3, either in one direction or the other. If 5 particles were spinning in one direction and 1 in the other, then the total spin would be 2, in one direction or the other. In short, if you have an even number of particles in a nucleus, each with a spin of plus 1/2 or minus 1/2, then the total spin is either 0 or a whole number, no matter what combination of positive and negative spins you choose. The total spin is always written as a positive number. On the other hand, suppose you have lithium-7, which was thought to be made up of 7 protons and 4 electrons. If the 7 protons were all plus 1/2 and the 4 electrons were all minus 1/2 in their spins, the nuclear spin would be 7/2 minus 4/2 equals 3/2. If you have an odd number of particles in the nucleus, you will find that any combination of positive and negative spins will never give you either 0 or a whole number as a sum. The sum will always include a fraction. Consequently, if one measures the spin of a particular atomic nucleus, one can tell at once whether that nucleus contains an even number of particles or an odd number.
This quickly raised a problem. The nuclear spin of the common isotope nitrogen-14 was measured accurately over and over again and turned out to be 1. There seemed no doubt about that, and it could therefore be concluded that there were an even number of particles in the nitrogen-14 nucleus. And yet, by the proton-electron theory of nuclear structure, the nitrogen-14 nucleus, with a mass number of 14 and an atomic number of 7, had to be made up of 14 protons and 7 electrons for a total of 21 particles altogether, an odd number. The nuclear spin of nitrogen-14 indicated even number, and the proton-electron theory indicated odd number. One or the other had to be wrong, but which? The nuclear spin was a matter of actual measurement which could be repeated over and over, and on which all agreed. The proton-electron theory was only a theory. It was therefore the latter that was questioned. What was to be done? Suppose it is wrong to count protons and electrons inside the nucleus as separate particles. Was it possible that an electron and a proton, forced into the close confinement of the atomic nucleus, might, by the force of mutual attraction, become so intimately connected as to count as a single particle? One of the first to suggest this, as far back as 1920, was Rutherford. Such a proton-electron combination would be electrically neutral, and in 1921 the American chemist William Draper Harkins, 1873 to 1951, used the term neutron as a name for it. If we look at the nitrogen-14 nucleus in this way, then it is made up not of 14 protons and 7 electrons, but of 7 protons and 7 proton-electron combinations. Instead of a total of 21 particles, there would be a total of 14. Instead of an odd number, there would be an even number. The structure would now account for the nuclear spin. But could such a revised theory of nuclear structure be made to seem plausible? The proton-electron theory seemed to make sense because both protons and electrons were known to exist separately and could be detected. If an intimate proton-electron combination could also exist, ought it not exist or be made to exist outside the nucleus, and ought it not be detected as an isolated particle? Discovery of the neutron. Throughout the 1920s, scientists searched for the neutron, but without success. One of the troubles was that the particle was electrically neutral. Subatomic particles could be detected in a variety of ways, but every single way, right down to the present time, makes use of their electric charge. The electric charge of a speeding subatomic particle either repels electrons or attracts them. In either case, electrons are knocked off atoms that are encountered by the speeding subatomic particle. The atoms with electrons knocked off are now positively charged ions. Droplets of water vapor can form about these ions, or a bubble of gas can form, or a spark of light can be seen. The droplets, the bubbles, and the light can all be detected one way or another, and the path of the subatomic particle could be followed by the trail of ions it left behind. Gamma rays, though they carry no charge, are a waveform capable of ionizing atoms. All the particles and rays that can leave a detectable track of ions behind are called ionizing radiation, and these are easy to detect. The hypothetical proton-electron combination, however, which was neither a wave form nor a charged particle, was not expected to be able to ionize atoms. It would wander among the atoms without either attracting or repelling electrons, and would therefore leave the atomic structure intact. Its pathway could not be followed. In short, then, the neutron was, so to speak, invisible, and the search for it seemed a lost cause. and until it was found, the proton-electron theory of nuclear structure, whatever its obvious deficiencies with respect to nuclear spin, remained the only one to work with. Then came 1930. The German physicist Walther Wilhelm Georg Botha, 1891 to 1957, and a co-worker, H. Becker, were bombarding the light metal beryllium with alpha particles. Ordinarily, they might expect protons to be knocked out of it, but in this case no protons appeared. They detected some sort of radiation because something was creating certain effects while the alpha particles were bombarding the beryllium, but not after the bombardment ceased. To try to determine something about the properties of this radiation, Botha and Becker tried putting objects in the way of the radiation. They found the radiation to be remarkably penetrating. It even passed through several centimeters of lead. The only form of radiation that was known at that time to come out of bombarded matter with the capacity of penetrating a thick layer of lead was gamma rays. Botha and Becker therefore decided they had produced gamma rays and reported this. In 1932, the Joliot-Curies repeated the Botha-Becker work and got the same results. However, among the objects they placed in the path of the new radiation, they included paraffin, which is made up of the light atoms of carbon and hydrogen. To their surprise, protons were knocked out of the paraffin. Gamma rays had never been observed to do this, but the Joliot-Curies could not think what else the radiation might be. They simply reported that they had discovered gamma rays to be capable of a new kind of action. Not so the English physicist James Chadwick, born 1891. In that same year, he maintained that a gamma ray which possessed no mass simply lacked the momentum to hurl a proton out of its place in the atom. Even an electron was too light to do so. It would be like trying to knock a baseball off the ground and into the air by hitting it with a ping-pong ball. Any radiation capable of knocking a proton out of an atom had to consist of particles that were themselves pretty massive. And if one argued like that, then it seemed that the radiation first observed by Botha and Becker had to be the long-sought-for proton-electron combination. Chadwick used Harkin's term, neutron, for it and made it official. He gets the credit for discovery of the neutron. Chadwick managed to work out the mass of the neutron from his experiments, and by 1934 it was quite clear that the neutron was more massive than the proton. The best modern data have the mass of the proton set at 1.007825, and that of the neutron just a trifle greater at 1.008665. The fact that the neutron was just about as massive as the proton was to be expected if the neutron were a proton-electron combination. It was also not surprising that the isolated neutron eventually breaks up, giving up an electron and becoming a proton. Out of any number of neutrons, half have turned into protons in about 12 minutes. Nevertheless, although in some ways we can explain the neutron by speaking of it as though it were a proton-electron combination, it really is not. A neutron has a spin of 1/2, while a proton-electron combination would have a spin of either 0 or 1. The neutron therefore must be treated as a single uncharged particle. The proton-neutron theory. As soon as the neutron was discovered, the German physicist Werner Karl Heisenberg, born 1901, revived the notion that the nucleus must be made up of protons and neutrons rather than protons and electrons. It was very easy to switch from the latter theory to the former if one simply remembered to pair the electrons thought to be in the nucleus with protons and give the name neutrons to these combinations. Thus, the helium-4 nucleus, rather than being made up of 4 protons and 2 electrons, was made up of 2 protons and 2 proton-electron combinations, or 2 protons and 2 neutrons. In the same way, the oxygen-16 nucleus, instead of being made up of 16 protons and 8 electrons, would be made up of 8 protons and 8 neutrons. The proton-neutron theory would account for mass numbers and atomic numbers perfectly well. If a nucleus was made up of X protons and Y neutrons, then the atomic number was equal to X and the mass number to X plus Y. It is now possible to define the mass number of a nucleus in modern terms. It is the number of protons plus neutrons in the nucleus. The proton-neutron theory of nuclear structure could account for isotopes perfectly well, too. Consider the 3 oxygen isotopes, oxygen-16, oxygen-17, and oxygen-18. The first would have a nucleus made up of 8 protons and 8 neutrons, the second one of 8 protons and 9 neutrons, and the third one of 8 protons and 10 neutrons. In each case, the atomic number is 8. The mass numbers, however, would be 16, 17, and 18, respectively. In the same way, uranium-238 would have a nucleus built of 92 protons and 146 neutrons, while uranium-235 would have one of 92 protons and 143 neutrons. By the new theory, can we suppose that it is neutrons rather than electrons that somehow hold the protons together against their mutual repulsion, and that more and more neutrons are required to do this as the nucleus grows more massive? At first, the number of neutrons required is roughly equal to the number of protons. The helium-4 nucleus contains 2 protons and 2 neutrons. The carbon-12 nucleus contains 6 protons and 6 neutrons. The oxygen-16 nucleus contains 8 protons and 8 neutrons, and so on. For more complicated nuclei, additional neutrons are needed. In vanadium-51, the nucleus contains 23 protons and 28 neutrons, 5 more than an equal amount. In bismuth-209, it is 83 protons and 126 neutrons, 43 more than an equal amount. For still more massive nuclei containing a larger number of protons, no amount of neutrons is sufficient to keep the assembly stable. The more massive nuclei are all radioactive. The manner of radioactive breakdown fits the theory too. Suppose a nucleus gives off an alpha particle. The alpha particle is a helium nucleus made up of 2 protons and 2 neutrons. If a nucleus loses an alpha particle, its mass number should decline by 4, and its atomic number by 2, and that is what happens. Suppose a nucleus gives off a beta particle. For a moment that might seem puzzling. If the nucleus contains only protons and neutrons and no electrons, where does the beta particle come from? Suppose we consider the neutrons as proton-electron combinations. Within many nuclei, the neutrons are quite stable and do not break up as they do in isolation. In the case of certain nuclei, however, they do break up. Thus, the thorium-234 nucleus is made up of 90 protons and 144 neutrons. One of these neutrons might be viewed as breaking up to liberate an electron and leaving behind an unbound proton. If a beta particle leaves, then, the number of neutrons decreases by 1 and the number of protons increases by 1. The thorium-234 nucleus, 90 protons, 144 neutrons, becomes a proactinium-234 nucleus, 91 protons, 143 neutrons. In short, the proton-neutron theory of nuclear structure could explain all the observed facts just as well as the proton-electron theory, and could explain the nuclear spins, which the proton-electron theory could not. What's more, the isolated neutron had been discovered. The proton-neutron theory was therefore accepted and remains accepted to this day. The nuclear interaction. In one place, and only one, did the proton-neutron theory seem a little weaker than the proton-electron theory. The electrons in the nucleus were thought to act as a kind of glue holding together the protons. But the electrons were gone. There were no negative charges at all inside the nucleus, only the positive charges of the proton, plus the uncharged neutron. As many as 83 positive charges were to be found in the bismuth 209 nucleus, squeezed together and yet not breaking apart. In the absence of electrons, what kept the protons clinging together? Was it possible that the electrical repulsion between two protons is replaced by an attraction if those protons were pushed together closely enough? Can there be both an attraction and a repulsion, with the former the more important at very short range? If this were so, that hypothetical attraction would have to have two properties. First, it would have to be extremely strong enough to overcome the repulsion of two positive charges at very close quarters. Secondly, it would have to be short range, for no attractive force between protons of any kind was ever detected outside the nucleus. In addition, this short-range attraction would have to involve the neutron. The hydrogen-1 nucleus was made up of a single proton, but all nuclei containing more than one proton had to contain neutrons also to be stable, and only certain numbers of neutrons. Until the discovery of the neutron, only two kinds of forces or interactions were known in the universe. These were the gravitational interaction and the electromagnetic interaction. The electromagnetic interaction was much the stronger of the two, trillions and trillions and trillions of times as strong as the gravitational attraction. The electromagnetic attraction, however, includes both attraction between opposite electric charges or between opposite magnetic poles, and repulsion between like electric charges or magnetic poles. In ordinary bodies, the attractions and repulsions usually cancel each other entirely or nearly entirely, leaving very little of one or the other to be detected as surplus. The gravitational interaction, however, includes only attraction, and this increases with mass. By the time you have gigantic masses, such as the Earth or the Sun, the gravitational interaction between them and other bodies is also gigantic. Both the gravitational and electromagnetic interactions are long-range. The intensity of each interaction declines with distance, but only as the square of the distance. If the distance between Earth and Sun were doubled, the gravitational interaction would still be 1/4 what it is now. If the distance were increased 10 times, the interaction would still be 1/10 times 10, or 1/100th what it is now. It is for this reason that gravitational and electromagnetic interactions can make themselves felt over millions of miles of space. But now, with the acceptance of the proton-neutron theory of nuclear structure, physicists began to suspect the existence of a third interaction, a nuclear interaction, much stronger than the electromagnetic interaction, perhaps 130 times as strong. Furthermore, the nuclear interaction had to decline very rapidly with distance, much more rapidly than the electromagnetic interaction did. In that case, protons in virtual contact, as within the nucleus, would attract each other, but if the distance between them was increased sufficiently to place one outside the nucleus, the nuclear interaction would decrease in intensity to less than the electromagnetic repulsion. The proton would now be repelled by the positive charge of the nucleus and would go flying away. That is why atomic nuclei have to be so small. It is only when they are so tiny that the nuclear interaction can hold them together. In 1932, Heisenberg tried to work out how these interactions might come into being. He suggested that attractions and repulsions were the result of particles being constantly and rapidly exchanged by the bodies experiencing the attractions and repulsions. Under some conditions, these exchange particles, moving back and forth very rapidly between two bodies, might force those bodies apart. Under other conditions, they might pull those bodies together. In the case of the electromagnetic interaction, the exchange particles seemed to be photons, wave packets that made up gamma rays, X-rays, or even ordinary light, all of which are examples of electromagnetic radiation. The gravitational interaction would be the result of exchange particles called gravitons. In 1969, there were reports that gravitons had actually been detected. Both the photon and the graviton have zero mass, and there is a connection between that and the fact that electromagnetic interaction and gravitational interaction decline only slowly with distance. For a nuclear interaction, which declines very rapidly with distance, the exchange particle, if any, would have to have mass. In 1935, the Japanese physicist Hideki Yukawa, born 1907, worked out in considerable detail the theory of such exchange particles in order to decide what kind of properties the one involved in the nuclear interaction would have. He decided it ought to have a mass about 250 times that of an electron, which would make it about 1/7 as massive as a proton. Since this mass is intermediate between that of an electron and proton, such particles eventually came to be called mesons, from a Greek word meaning intermediate. Once Yukawa published his theory, the search was on for the hypothetical mesons. Ideally, if they existed within the nucleus, shooting back and forth between protons and neutrons, there ought to be some way of knocking them out of the nucleus and studying them in isolation. Unfortunately, the bombarding particles at the disposal of physicists in the 1930s possessed far too little energy to knock mesons out of nuclei, assuming they were there in the first place. There was one way out. In 1911, the Austrian physicist Victor Francis Hess, 1883 to 1964, had discovered that Earth was bombarded from every side by cosmic rays. These consisted of speeding atomic nuclei, cosmic particles, of enormous energies, in some cases billions of times as intense as any energies available through particles produced by mankind. If a cosmic particle of sufficient energy struck an atomic nucleus in the atmosphere, it might knock mesons out of it. In 1936, the American physicists Carl David Anderson, born 1905, and Seth Henry Nettermeyer, born 1907, studying the results of cosmic particle bombardment of matter, detected the existence of particles of intermediate mass. This particle turned out to be lighter than Yukawa had predicted. It was only about 207 times as massive as an electron. Much worse, it lacked other properties that Yukawa had predicted. It did not interact with the nucleus in the manner expected. In 1947, however, the English physicist Cecil Frank Powell 1903 to 1969, and his co-workers, also studying cosmic particle bombardment, located another intermediate-sized body, which had the right mass and all the other appropriate properties to fit Yukawa's theories. Anderson's particle was called a mu meson, soon abbreviated to muon. Powell's particle was called a pi meson, soon abbreviated to pion. With the discovery of the pion, Yukawa's theory was nailed down, and any lingering doubt as to the validity of the proton-neutron theory vanished. Actually, it turns out that there are two forces. The one with the pion as exchange particle is the strong nuclear interaction. Another, involved in beta particle emission, for instance, is a weak interaction, much weaker than the electromagnetic, but stronger than the gravitational. The working out of the details of the strong nuclear interaction explains further the vast energies to be found resulting from nuclear reactions. Ordinary chemical reactions, with the electron shifts that accompany them, involve the electromagnetic interaction only. Nuclear energy, with the shifts of the particles inside the nucleus, involves the much stronger nuclear interaction. Neutron bombardment. As soon as neutrons were discovered, it seemed to physicists that they had another possible bombarding particle of extraordinary properties. Since the neutron lacked any electric charge, it could not be repelled by either electrons on the outside of the atoms or by the nuclei at the center. The neutron was completely indifferent to the electromagnetic attraction, and it just moved along in a straight line. If it happened to be headed toward a nucleus, it would strike it, no matter how heavy a charge that nucleus might have, and very often it would, as a result, induce a nuclear reaction where a proton would not have been able to. To be sure, it seemed just at first that there was a disadvantage to the neutron's lack of charge. It could not be accelerated directly by any device, since that always depended on electromagnetic interaction, to which the neutron was impervious. There was one way of getting around this, and this was explained in 1935 by the American physicist J. Robert Oppenheimer, 1904 to 1967, and by his student Melba Phillips. Use is made here of the nucleus of the hydrogen-2 deuterium nucleus. That nucleus, often called a deuteron, is made up of one proton plus one neutron, and has a mass number of 2 and an atomic number of 1. Since it has a unit positive charge, it can be accelerated just as an isolated proton can be. Suppose, then, that a deuteron is accelerated to a high energy and is aimed right at a positively charged nucleus. That nucleus repels the deuteron, and it particularly repels the proton part. The nuclear interaction that holds together a single proton and a single neutron is comparatively weak as nuclear interactions go, and the repulsion of the nucleus that the deuteron is approaching may force the proton out of the deuteron altogether. The proton veers off, but the neutron, unaffected, keeps right on going, and, with all the energy it had gained as part of the deuteron acceleration, smashes into the nucleus. Within a few months of their discovery, energetic neutrons were being used to bring about nuclear reactions. Actually, though, physicists didn't have to worry about making neutrons energetic. This was a hangover from their work with positively charged particles, such as protons and alpha particles. These charged particles had to be energetic to overcome the repulsion of the nucleus and to smash into it with enough force to break it up. Neutrons, however, didn't have to overcome any repulsion. No matter how little energy they had, if they were correctly aimed, and some always were through sheer chance, they would approach and strike the nucleus. In fact, the more slowly they traveled, the longer they would stay in the vicinity of a nucleus, and the more likely they were to be captured by some nearby nucleus through the attraction of the nuclear interaction. The influence of the nucleus in capturing the neutron was greater the slower the neutron, so that it was almost as though the nucleus were larger and easier to hit for a slow neutron than a fast one. Eventually, physicists began to speak of nuclear cross-sections, and to say that particular nuclei had a cross-section of such and such a size for this bombarding particle or that. The effectiveness of slow neutrons was discovered in 1934 by the Italian-American physicist Enrico Fermi, 1901 to 1954. Of course, there was the difficulty that neutrons couldn't be slowed down once they were formed, and as formed they generally had too much energy, according to the new way of looking at things. At least they couldn't be slowed down by electromagnetic methods, but there were other ways. A neutron didn't always enter a nucleus that it encountered. Sometimes, if it struck the nucleus a hard, glancing blow, it bounced off. If the nucleus struck by the neutron is many times as massive as the neutron bounced off with all its speed practically intact. On the other hand, if the neutron hits a nucleus not very much more massive than itself, the nucleus rebounds and absorbs some of the energy, so that the neutron bounces away with less energy than it had. If the neutron rebounds from a number of comparatively light nuclei, it eventually loses virtually all its energy, and finally moves about quite slowly, possessing no more energy than the atoms that surround it. You can encounter this situation in ordinary life in the case of billiard balls. A billiard ball colliding with a cannonball will just bounce, moving just as rapidly afterward as before, though in a different direction. If a billiard ball strikes another billiard ball, it will set the target ball moving and bounce off itself with less speed. The energy of the molecules in the atmosphere depends on temperature. Neutrons that match that energy and have the ordinary quantity to be expected at room temperature are called thermal, from a Greek word meaning heat, neutrons. The comparatively light nuclei against which the neutrons bounce and slow down are moderators, because they moderate the neutron's energy. Fermi and his co-workers were the first to moderate neutrons, produce thermal neutrons, and use them in 1935 to bombard nuclei. He quickly noted how large nuclear cross-sections became when thermal neutrons were the bombarding particles. It might seem that hope could now rise in connection with the practical use of energy derived from nuclear reactions. Neutrons could bring about nuclear reactions even when they themselves possessed very little energy, so output might conceivably be more than input for each neutron that struck. Furthermore, because of the large cross-sections involved, thermal neutrons missed far less frequently than high-energy charged particles did. But there was a catch. Before neutrons could be used, however low energy and however sure to hit, they had to be produced. And in order to produce neutrons, they had to be knocked out of nuclei by bombardment with high-energy protons or some other method. The energy formed by the neutrons was at first never more than the tiniest fraction of the energies that went into forming the neutrons in the first place. It was as though you could indeed light a candle with a single match, but you still had to look through 300,000 useless pieces of wood before you found a match. The candle would still be impractical. Even with the existence of neutron bombardment, involving low energy and high cross-section, Rutherford could, with justice, feel right down to the time of his death that nuclear energy would never be made available for practical use. And yet, among the experiments that Fermi was trying in 1934 was that of sending his neutrons crashing into uranium atoms. Rutherford had no way of telling, and neither had Fermi, that this, finally, was the route to the unimaginable. End of section 4. Section number 5 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. Nuclear Fission. New Elements. In 1934, Enrico Fermi began his first experiments involving the bombardment of uranium with neutrons, experiments that were to change the face of the world. Fermi had found that slow neutrons, which had very little energy, were easily absorbed by atomic nuclei, more easily than fast neutrons were absorbed, and certainly more easily than charged particles were. Often what happened was that the neutron was simply absorbed by the nucleus. Since the neutron has a mass number of 1 and an atomic number of 0, because it is uncharged, a nucleus that absorbs a neutron remains an isotope of the same element, but increases its mass number. For instance, suppose that neutrons are used to bombard hydrogen-1, which then captures one of the neutrons. From a single proton, it will become a proton plus a neutron. From hydrogen-1, it will become hydrogen-2. A new nucleus formed in this way will be at a higher energy, and that energy is emitted in the form of a gamma ray. Sometimes the more massive isotope that is formed through neutron absorption is stable, as hydrogen-2 is. Sometimes it is not, but is radioactive instead. Because it has added a neutron, it has too many neutrons for stability. The best way of adjusting the matter is to emit a beta particle, electron. This converts one of the neutrons into a proton. The mass number stays the same, but the atomic number increases by 1. The element rhodium, for example, which has an atomic number of 45, has only one stable isotope, with a mass number of 103. If rhodium-103, 45 protons, 58 neutrons, absorbs a neutron, it becomes rhodium-104, 45 protons, 59 neutrons, which is not stable. Rhodium-104 emits a beta particle, changing a neutron to a proton so that the nuclear combination becomes 46 protons and 58 neutrons. This is palladium-104, which is stable. As another example, indium-115, 49 protons, 66 neutrons, absorbs a neutron and becomes indium-116, 49 protons, 67 neutrons, which gives off a beta particle and becomes tin-116, 50 protons, 66 neutrons, which is stable. There are over 100 isotopes that will absorb neutrons and end by becoming an isotope of an element 1 higher in the atomic number scale. Fermi observed a number of these cases. Having done so, he was bound to ask what would happen if uranium were bombarded with neutrons. Would its isotopes also be raised in atomic number, in this case from 92 to 93? If that were so, it would be very exciting, for uranium had the highest atomic number in the entire scale. Nobody had ever discovered any sample of element number 93, but perhaps it could be formed in the laboratory. In 1934, therefore, Fermi bombarded uranium with neutrons in the hope of obtaining atoms of element 93. Neutrons were absorbed, and whatever was formed did give off beta particles, so element 93 should be there. However, 4 different kinds of beta particles, different in their energy content, were given off, and the matter grew very confusing. Fermi could not definitely identify the presence of atoms of element 93, and neither could anyone else for several years. Other things turned up, however, which were even more significant. Before going on to these other things, however, it should be mentioned that undoubtedly element 93 was formed, even though Fermi couldn't clearly demonstrate the fact. In 1939, the American physicists Edwin Madison Macmillan, born 1907, and Philip Haug Abelson, born 1913, after bombarding uranium atoms with slow neutrons, were able to identify element 93. Since uranium had originally been named for the planet Uranus, the new element, beyond uranium, was eventually named for the planet Neptune, which lay beyond Uranus. Element 93 is therefore called Neptunium. What happened was exactly what was expected. Uranium-238, 92 protons, 146 neutrons, added a neutron to become uranium-239, 92 protons, 147 neutrons, which emitted a beta particle to become Neptunium-239, 93 protons, 146 neutrons. In fact, Neptunium-239 also emitted a beta particle, so it ought to become an isotope of an element even higher in the atomic number scale. This one, element 94, was named plutonium after Pluto, the planet beyond Neptune. The isotope plutonium-239, formed from Neptunium-239, was only feebly radioactive, however, and it was not clearly identified until 1941. The actual discovery of the element plutonium came a year before, however, when Neptunium-238 was formed. It emitted a beta particle and became plutonium-238, an isotope that was radioactive enough to be easily detected and identified by Glenn Theodore Seaborg, born 1912, and his co-workers, who completed Macmillan's experiments when he was called away to other defense research. Neptunium and plutonium were the first trans-uranium elements to be produced in the laboratory, but they weren't the last. Over the next 30 years, isotopes were formed that contained more and more protons in the nucleus and therefore had higher and higher atomic numbers. At the moment of writing, isotopes of every element up to and including element 105 have been formed. A number of these new elements have been named for some of the scientists important in the history of nuclear research. Element 96 is curium, named for Pierre and Marie Curie. Element 99 is Einsteinium, for Albert Einstein, and element 100 is fermium, for Enrico Fermi. Element 101 is Mendelevium, for the Russian chemist Dmitry Mendeleev, who early in 1869 was the first to arrange the elements in a reasonable and useful order. Element 103 is Lawrencium, for Ernest O. Lawrence. Rutherfordium, for Ernest Rutherford, has been proposed for element 104. And Hahnium, for Otto Hahn, 1879 to 1968, a German physical chemist whose contribution we will come to shortly, has been proposed for element 105. Neptunium, however, was not the first new element to be created in the laboratory. In the early 1930s, there were still 2 elements with fairly low atomic numbers that had never been discovered. These were the elements with atomic numbers 43 and 61. In 1937, though, molybdenum, atomic number 42, had been bombarded with neutrons in Lawrence's laboratory in the United States. It might contain small quantities of element 43 as a result. The Italian physicist Emilio Segre, born 1905, who had worked with Fermi, obtained a sample of the bombarded molybdenum and indeed obtained indications of the presence of element 43. It was the first new element to be manufactured by artificial means and was called technetium, from the Greek word for artificial. The technetium isotope that was formed was radioactive. Indeed, all the technetium isotopes are radioactive. Element 61, discovered in 1945 and named promethium, also has no stable isotopes. Technetium and promethium are the only elements with atomic numbers less than 84 that do not have even a single stable isotope. The discovery of fission. But let us get back to the bombardment of uranium with neutrons research that Fermi had begun. After he had reported his work, other physicists repeated it and also got a variety of beta particles and were also unable to decide what was going on. One way to tackle the problem was to add to the system some stable element that was chemically similar to the tiny traces of radioactive isotopes that might be produced through the bombardment of uranium. Afterwards, the stable element could probably be separated out of the mixture, and the trace of radioactivity would, it was hoped, be carried along with it. The stable element would be a carrier. Among those working on the problem were Otto Hahn and his Austrian co-worker, the physicist Lise Meitner, 1878 to 1968. Among the potential carriers they added to the system was the element barium, which has an atomic number of 56. They found that a considerable quantity of the radioactivity did indeed accompany the barium when they separated that element out of the system. A natural conclusion was that the isotopes producing the radioactivity belonged to an element that was chemically very similar to barium. Suspicion fell at once on radium, atomic number 88, which was very like barium indeed as far as chemical properties were concerned. Lise Meitner, who was Jewish, found it difficult to work in Germany, however, for it was then under the rule of the strongly anti-Semitic Nazi regime. In March 1938, Germany occupied Austria, which became part of the German realm. Meitner was no longer protected by her Austrian citizenship and had to flee the country and go to Stockholm, Sweden. Hahn remained in Germany and continued working on the problem with the German physical chemist Fritz Strassmann, born 1902. Although the supposed radium which possessed the radioactivity was very like barium in chemical properties, the two were not entirely identical. There were ways of separating them, and Hahn and Strassmann busied themselves in trying to accomplish this in order to isolate the radioactive isotopes, concentrate them, and study them in detail. Over and over again, however, they failed to separate the barium and the supposed radium. Slowly, it began to seem to Hahn that the failure to separate the barium and the radioactivity meant that the isotopes to which the radioactivity belonged had to be so much like barium as to be nothing else but barium. He hesitated to say so, however, because it seemed unbelievable. If the radioactive isotopes included radium, that was conceivable. Radium had an atomic number of 88, only 4 less than uranium's 92. You could imagine that a neutron being absorbed by a uranium nucleus might make the latter so unstable as to cause it to emit 2 alpha particles and become radium. Barium, however, had an atomic number of 56, only a little over half that of uranium. How could a uranium nucleus be made to turn into a barium nucleus unless it more or less broke in half? Nothing like that had ever been observed before, and Hahn hesitated to suggest it. While he was nerving himself to do so, however, Lisa Meitner, in Stockholm, receiving reports of what had been done in Hahn's laboratory and thinking about it, decided that, unheard of or not, there was only one explanation. The uranium nucleus was breaking in half. Actually, when one stopped to think of it after getting over the initial shock, it wasn't so unbelievable at that. The nuclear force is so short range it barely reaches from end to end of a large nucleus like that of uranium. Left to itself, it holds together most of the time, but with the added energy of an entering neutron, we might imagine shock waves going through it and turning the nucleus into something like a quivering drop of liquid. Sometimes the uranium nucleus recovers, keeps the neutron, and then goes on to beta particle emission. And sometimes the nucleus stretches to the point where the nuclear force doesn't quite hold it together. It becomes a dumbbell shape, and then the electromagnetic repulsion of the 2 halves, both positively charged, breaks it apart altogether. It doesn't break into equal halves, nor does it always break at exactly the same place, so that there were a number of different fragments possible, which was why there was so much confusion. Still, one of the more common ways in which it might break would be into barium and krypton. Their respective atomic numbers, 56 and 36, would add up to 92. Meitner and her nephew Otto Robert Frisch, born 1904, who was in Copenhagen, Denmark, prepared a paper suggesting that this was what was happening. It was published in January 1939. Frisch passed it on to the Danish physicist Niels Bohr, 1885 to 1962, with whom he was working. The American biologist William Archibald Arnold, born 1904, who was also working in Copenhagen at the time, suggested that the splitting of the uranium nucleus into halves be called fission, the term used for the division in 2 of living cells. The name stuck. In 1939, just about the time Meitner and Frisch's paper was published, Bohr had arrived in the United States to attend a conference of physicists. He carried the news of fission with him. The other physicists attending the conference heard the news and, in a high state of excitement, at once set about studying the problem. Within a matter of weeks, the fact of uranium fission was confirmed over and over. One striking fact about uranium fission was the large amount of energy it released. In general, when a very massive nucleus is converted to a less massive one, energy is released because of the change in the mass defect, as Aston had shown in the 1920s. When the uranium nucleus breaks down through the ordinary radioactive processes to become a less massive lead nucleus, energy is given off accordingly. When, however, it breaks in 2 to become the much less massive nuclei of barium and krypton, or others in that neighborhood, much more energy is given off. It quickly turned out that uranium fission gave off something like 10 times as much nuclear energy per nucleus than did any other nuclear reaction known at the time. Even so, the quantity of energy released by uranium fission was only a tiny fraction of the energy that went into the preparation of the neutrons used to bring about the fission. if each neutron that struck a uranium atom brought about a single fission of that one atom. Under these conditions, Rutherford's suspicion that mankind would never be able to tap nuclear energy probably still remained true. He had been dead for 2 years at the time of the discovery of fission. However, those were not the conditions. The nuclear chain reaction. Earlier in this history, we discussed chain reactions involving chemical energy. A small bit of energy can ignite a chemical reaction that would produce more than enough energy to ignite a neighboring section of the system, which would in turn produce still more, and so on and so on. In this way, the flame of a single match could start a fire in a leaf that would burn down an entire forest, and the energy given off by the burning forest would be enormously higher than the initial energy of the match flame. Might there not be such a thing as a nuclear chain reaction? Could one initiate a nuclear reaction that would produce something that would initiate more of the same, that would produce something that would initiate still more of the same, and so on? In that case, a nuclear reaction, once started, would continue of its own accord, and in return for the trifling investment that would serve to start it, a single neutron perhaps, a vast amount of breakdowns would result with the delivery of a vast amount of energy. Even if it were necessary to expend quite a bit of energy to produce the one neutron that would start the chain reaction, one would end with an enormous profit. What's more, since the nuclear reaction would spread from nucleus to nucleus with millionths of a second intervals, there would be in a very brief time so many nuclei breaking down that there would be a vast explosion. The explosion was sure to be millions of times as powerful as ordinary chemical explosions involving the same quantity of exploding material, since the latter used only the electromagnetic interaction while the former used the much stronger nuclear interaction. The first to think seriously of such a nuclear chain reaction was the Hungarian physicist Leo Szilard, 1898 to 1964. He was working in Germany in 1933 when Adolf Hitler came to power, and, since he was Jewish, he felt it would be wise to leave Germany. He went to Great Britain, and there, in 1934, he considered certain new types of nuclear reactions that had been discovered. In these, it sometimes happened that a fast neutron might strike a nucleus with sufficient energy to cause it to emit 2 neutrons. In that way, the nucleus absorbing 1 neutron and emitting 2 would become a lighter isotope of the same element. But what would happen if each of the 2 neutrons that emerged from the original target nucleus struck new nuclei and forced the emission of a pair of neutrons from each? There would now be a total of 4 neutrons flying about, and if each struck new nuclei there would next be 8 neutrons, and so on. From the initial investment of a single neutron, there might soon be countless billions initiating nuclear reactions. Szilard, fearing the inevitability of war, and fearing further that the brutal leaders of Germany might seek and use such a nuclear chain reaction as a weapon in warfare, secretly applied for a patent on a device intending to make use of such a nuclear chain reaction. He hoped to turn it over to the British government, which might then use its possession as a way of restraining the Nazis and keeping the peace. However, it wouldn't have worked. It took the impact of a very energetic neutron to bring about the emission of 2 neutrons. The neutrons that then emerged from the nucleus simply didn't have enough energy to keep things going. It was like trying to make wet wood catch fire. But what about uranium fission? Uranium fission was initiated by slow neutrons. What if uranium fission also produced neutrons as well as being initiated by a neutron? Would not the neutrons produced serve to initiate new fissions that would produce new neutrons, and so on endlessly? It seemed very likely that fission produced neutrons, and indeed, Fermi at the conference where fission was first discussed suggested it at once. Massive nuclei possessed more neutrons per proton than less massive ones did. If a massive nucleus was broken up into two considerably less massive ones, there would be a surplus of neutrons. Suppose, for instance, uranium-238 broke down into barium-138 and krypton-86. Barium-138 contains 82 neutrons, and krypton-86 50 neutrons, for a total of 132. The uranium-238 nucleus, however, contains 146 neutrons. The uranium fission process was studied at once to see if neutrons were actually given off, and a number of different physicists, including Szilard, found that they were. Now Szilard was faced with a nuclear chain reaction he was certain would work. Only slow neutrons were involved, and the individual nuclear breakdowns were far more energetic than anything else that had yet been discovered. If a chain reaction could be started in a sizable piece of uranium, unimaginable quantities of energy would be produced. Just 1 gram of uranium undergoing complete fission would deliver the energy derived from the total burning of 3 tons of coal, and would deliver that energy in a tiny fraction of a second. Szilard, who had come to the United States in 1937, clearly visualized the tremendous explosive force of something that would have to be called a nuclear bomb. Szilard dreaded the possibility that Hitler might obtain the use of such a bomb through the agency of Germany's nuclear scientists. Partly through Szilard's efforts, physicists in the United States and in other Western nations opposed to Hitler began a program of voluntary secrecy in 1940 to avoid passing along any hints to Germany. What's more, Szilard enlisted the services of 2 other Hungarian refugees, the physicists Eugene Paul Wigner, born 1902, and Edward Teller, born 1908, and all approached Einstein, who had also fled Germany and come to America. Einstein was the most prestigious scientist then living, and it was thought a letter from him to the President of the United States would be most persuasive. Einstein signed such a letter, which explained the possibility of a nuclear bomb and urged that the United States not allow a potential enemy to come into possession of it first. Largely as a result of this letter, a huge research team was put together in the United States, to which other Western nations also contributed, with but one aim: to develop the nuclear bomb. Albert Einstein, Old Grove Road, Nassau Point, Peconic, Long Island, August 2nd, 1939. F.D. Roosevelt, President of the United States, White House, Washington, D.C. Sir, some recent work by E. Fermi and L. Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration.
I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable, through the work of Joliot in France as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by boat and exploded in a port, might very well destroy the whole port together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. The United States has only very poor ores of uranium in moderate quantities. There is some good ore in Canada and the former Czechoslovakia, while the most important source of uranium is Belgian Congo. In view of this situation, you may think it desirable to have some permanent contact maintained between the administration and the group of physicists working on chain reactions in America. One possible way of achieving this might be for you to entrust with this task a person who has your confidence and who could perhaps serve in an unofficial capacity. His task might comprise the following: A. To approach government departments, keep them informed of the further development, and put forward recommendations for government action, giving particular attention to the problem of securing a supply of uranium ore for the United States. B. To speed up the experimental work which is at present being carried on within the limits of the budgets of university laboratories, by providing funds, if such funds be required, through his contacts with private persons who are willing to make contributions for this cause, and perhaps also by obtaining the cooperation of industrial laboratories which have the necessary equipment. I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of the German Undersecretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated. Yours very truly, Albert Einstein.
The nuclear bomb. Although the theory of the nuclear bomb seemed clear and simple, a great many practical difficulties stood in the way. In the first place, if only uranium atoms underwent fission, a supply of uranium had at least to be obtained in pure form, for if the neutrons struck nuclei of elements other than uranium, they would simply be absorbed and removed from the system, ending the possibility of a chain reaction. This alone was a heavy task, since there had been so little use for uranium in quantity that there was almost no supply in existence and no experience in how to purify it. Second, the supply of uranium might have to be a large one, for neutrons didn't necessarily enter the first uranium atom they approached. They moved about here and there, making glancing collisions and traveling quite a distance perhaps, before striking head-on and entering a nucleus.
If in that time they had passed outside the lump of uranium, they were useless. As the quantity of uranium within which the fission chain reaction was initiated grew larger, more and more of the neutrons produced found a mark, and the fission reaction would die out more and more slowly. Finally, at some particular size, the critical size, the fission reaction did not die at all, but maintained itself, with enough of the neutrons produced finding their mark to keep the nuclear reaction proceeding at a steady rate. At any greater size, the nuclear reaction would accelerate, and there would be an explosion. It wasn't even necessary to send neutrons into the uranium to start the process. In 1941, the Russian physicist Georgy Nikolaevich Flerov, born 1913, found that every once in a while a uranium atom would undergo fission without the introduction of a neutron. Occasionally, the random quivering of a nucleus would bring about a shape that the nuclear interaction could not bring back to normal, and the nucleus would then break apart. In a gram of ordinary uranium, there is a nucleus undergoing such spontaneous fission every 2 minutes on the average. Therefore, enough uranium need only be brought together to surpass critical size, and it will explode within seconds. For the first nucleus that undergoes spontaneous fission will start the chain reaction. First estimates made it seem that the quantity of uranium needed to reach critical size was extraordinarily great. Fully 99.3% of the metal is uranium-238, however, and as soon as fission was discovered, Bohr pointed out that there were theoretical reasons for supposing that it was the uranium-235 isotope, making up only 0.7% of the whole, that was the one undergoing fission. Investigation proved him right. Indeed, the uranium-238 nucleus tended to absorb slow neutrons without fission, and then go on to beta particle production that formed isotopes of neptunium and plutonium. In this way, uranium-238 actually interfered with the chain reaction. In any quantity of uranium, the more uranium-235 present and the less uranium-238, the more easily the chain reaction would proceed and the lower the critical size needed. Vast efforts were therefore made to separate the two isotopes and prepare uranium with a higher than normal concentration of uranium-235, enriched uranium. Of course, there was no great desire for a fearful explosion to get out of hand while the chain reaction was being studied. Before any bomb could be constructed, the mechanism of the chain reaction would have to be studied. Could a chain reaction capable of producing energy for useful purposes as well as for bombs be established? To test this, a quantity of uranium was gathered in the hope that a controlled chain reaction of uranium fission could be established. For that purpose, control rods of a substance that would easily absorb neutrons and slow the chain reaction were used. The metal, cadmium, served admirably for this purpose. Then, too, the neutrons released by fission were pretty energetic. They tended to travel too far too soon and get outside the lump of uranium too easily. To produce a chain reaction that could be studied with some safety, the presence of a moderator was needed. This was a supply of small nuclei that did not absorb neutrons easily, but absorbed some of the energy of collision and slowed down any neutron that struck it. Nuclei such as hydrogen-2, beryllium-9, or carbon-12 were useful moderators. When the neutrons produced by fission were slowed, they traveled a smaller distance before being absorbed in their turn, and the critical size would again be reduced. Toward the end of 1942, the initial stage of the project reached a climax. Blocks of graphite containing uranium metal and uranium oxide were piled up in huge quantities. Enriched uranium was not yet available, in order to approach critical size. This took place under the stands of a football stadium at the University of Chicago, with Enrico Fermi, who had come to the United States in 1938, in charge. The large structure was called an atomic pile at first, because of the blocks of graphite being piled up. The proper name for such a device, and the one that was eventually adopted, was, however, nuclear reactor. On December 2, 1942, calculations showed that the nuclear reactor was large enough to have reached critical size. The only thing preventing the chain reaction from sustaining itself was the cadmium rods that were inserted here and there in the pile, and that were soaking up neutrons. One by one, the cadmium rods were pulled out. The number of uranium atoms undergoing fission each second rose, and finally, at 3:45 p.m., the uranium fission became self-sustaining. It kept going on its own, with the cadmium rods ready to be pushed in if it looked as though it were getting out of hand, something calculations showed was not likely. News of this success was announced to Washington by a cautious telephone call from Arthur Holly Compton, 1892 to 1962, to James Bryant Conant, born 1893. Quote, "The Italian navigator has landed in the New World," unquote, said Compton. Conant asked, quote, "How were the natives?" unquote, and the answer was, quote, "very friendly," unquote. This was the day and moment when the world entered the nuclear age. For the first time, mankind had constructed a device in which the nuclear energy being given off was greater than the energy poured in. Mankind had tapped the reservoirs of nuclear energy and put it to use. Had Rutherford lived but 6 more years, he would have seen how wrong he was to think it could never be done. The people of Earth remained unaware of what had taken place in Chicago, and physicists continued to work toward the development of the nuclear bomb. Enriched uranium was successfully prepared. Critical sizes were brought low enough to make a nuclear bomb small enough to be carried by plane to some target. Suppose one had 2 slabs of enriched uranium, each below critical size, but which were above critical size if combined. And suppose an explosive device were added that, at some desired moment, could be set off in such a way that it would drive one slab of enriched uranium against the other. There would be an instant explosion of devastating power. Or, suppose the enriched uranium were arranged in loosely packed pieces to begin with, so that the flying neutrons were in open air too often to maintain the chain reaction. A properly arranged explosion might compress the uranium into a dense ball. Neutron absorption would become more efficient, and again an explosion would follow. On July 16, 1945, a device that would result in a nuclear explosion was set up near Alamogordo, New Mexico, with nervous physicists watching from a safe distance. It worked perfectly. The explosion was tremendous. By that time, Nazi Germany had been defeated, but Japan was still fighting. 2 more devices were prepared. After a warning, one was exploded over the Japanese city of Hiroshima on August 6, 1945, and the other over Nagasaki 2 days later. The Japanese government surrendered and World War II came to an end. It was with the blast over Hiroshima that the world came to know it was in the nuclear age and that the ferocious weapon of the nuclear bomb existed. The popular name for it at the time was atomic bomb or A-bomb. During the war, German scientists may have been trying to develop a nuclear bomb, but if so, they had not yet succeeded at the time Germany met its final defeat. Soviet physicists under Igor Vasilievich Kurchatov, 1903 to 1960, were also working on the problem. The dislocation of the war, which inflicted much more damage on the Soviet Union than on the United States, kept the Soviet effort from succeeding while it was on. However, since the Soviets were among the victors, they were able to continue after the war. In 1949, the Soviets exploded their first nuclear bomb. In 1952, the British did the same. In 1960, the French, and in 1964, the Chinese. Although many nuclear bombs have been exploded for test purposes, the 2 over Hiroshima and Nagasaki have been the only ones used in time of war. Nor need nuclear bombs be considered as having destructive potential only. There is the possibility that, with proper precautions, they might be used to make excavations, blast out harbors or canals, break up underground rock formations to recover oil or other resources, and in other ways do the work of chemical explosives with far greater speed and economy. It has even been suggested that a series of nuclear bomb explosions might be used to hurl space vehicles forward in voyages away from Earth. Nuclear reactors. The development of the nuclear chain reaction was not in the direction of bombs only. Nuclear reactors designed for the controlled production of useful energy multiplied in number and in efficiency since Fermi's first pile. Many nations now possess them, and they are used for a variety of purposes. In 1954, the first nuclear submarine, the USS Nautilus, was launched by the United States. Its power was obtained entirely from a nuclear reactor, and it was not necessary for it to rise to the surface at short intervals in order to recharge its batteries. Nuclear submarines have crossed the Arctic Ocean under the ice cover and have circumnavigated the globe without surfacing. In 1959, both the Soviet Union and the United States launched nuclear-powered surface vessels. The Soviet ship was the icebreaker Lenin, and the American ship was a merchant vessel, the NS Savannah. In the 1950s, nuclear reactors were also used as the source of power for the production of electricity for civilian use. The Soviet Union built a small station of this sort in 1954, which had a capacity of 5,000 kilowatts. The British built one of 92,000 kilowatt capacity, which they called Calder Hall. The first American nuclear reactor for civilian use began operation at Shippingport, Pennsylvania in 1958. It was the first really full-scale civilian nuclear power plant in the world. The world appeared to have far greater resources of energy than had been expected. The fossil fuels, coal, oil, and natural gas, were being used at such a rate that many speculated that the gas and oil would be gone in decades and the coal in centuries. Was it possible that uranium might now serve as a new source that would last indefinitely? It was rather disappointing that it was uranium-235 which underwent fission, because that isotope made up only 0.7% of the uranium that existed. If uranium-235 were all we had and all we ever could have, the energy supply of the world would still be rather too limited. There were other possible nuclear fuels, however. There was plutonium-239, which would also fission under neutron bombardment. It had an ordinary half-life for a radioactive change in which it gave off alpha particles of 24,300 years, which is long enough to make it easy to handle. But how can plutonium-239 be formed in sufficient quantities to be useful? After all, it doesn't occur in nature. Surprisingly, that turned out to be easy. Uranium-238 atoms will absorb many of the neutrons that are constantly leaking out of the reactor and will become first Neptunium-239 and then Plutonium-239. The plutonium, being a different element from the uranium, can be separated from uranium and obtained in useful quantities. Such a device is called a breeder reactor because it breeds fuel. Indeed, it can be so designed to produce more plutonium-239 than the uranium-235 it uses up, so that you actually end up with more nuclear fuel than you started with. In this way, all the uranium on Earth, and not just uranium-235, can be considered potential nuclear fuel. The first breeder reactor was completed at Arco, Idaho, in August 1951, and on December 20, produced the very first electricity on Earth to come from nuclear power. Nevertheless, breeder reactors for commercial use are still a matter for the future. Another isotope capable of fissioning under nuclear bombardment is uranium-233. It does not occur in nature, but was formed in the laboratory by Seaborg and others in 1942. It has a half-life of 162,000 years. It can be formed from naturally occurring thorium-232. Thorium-232 will absorb a neutron to become thorium-233. Then 2 beta particles are given off, so that the thorium-233 becomes first proactinium-233 and then uranium-233. If a thorium shell surrounds a nuclear reactor, fissionable uranium-233 is formed within it and is easily separated from the thorium. In this way, thorium is also added to the list of Earth's potential nuclear fuels. If all the uranium and thorium in the Earth's crust, including the thin scattering of those elements through granite, for instance, were available for use, we might get up to 100 times as much energy from it as from all the coal and oil on the planet. Unfortunately, it is very unlikely that we will ever be able to make use of all the uranium and thorium. It is widely and thinly spread through the crustal rocks, and much of it could not be extracted without using up more energy than would be supplied by it once isolated. Another problem rests with the nature of the fission reaction. When the uranium-235 nucleus, or plutonium-239, or uranium-233, undergoes fission, it breaks up into any of a large number of middle-sized nuclei that are radioactive, much more intensely radioactive than the original fuel. It was from among these fission products that isotopes of element 61 were first obtained in 1945. Coming from the nuclear fire, it reminded its discoverers of Prometheus, who stole fire from the sun in the Greek myths, and so it was called Prometheum. The fission products still contain energy, and some of them can be used in lightweight nuclear batteries. Such nuclear batteries were first built in 1954. Some batteries using plutonium-238 rather than fission products have been put to use in powering artificial satellites over long periods. Unfortunately, only a small proportion of the fission products can be put to profitable use. Most must be disposed of. They are dangerous because the radiations they give off are deadly and cannot be detected by the ordinary senses. They are very difficult to dispose of safely, and they must not be allowed to get into the environment, especially since some of them remain dangerous for decades or even centuries.
End of Section 5. Section number 6 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. Nuclear fusion. The energy of the sun. As it happens, though, nuclear fission is not the only route to useful nuclear energy. Aston's studies in the 1920s had shown that it was the middle-sized nuclei that were most tightly packed. Energy would be given off if middle-sized nuclei were produced from either extreme. Not only would energy be formed by the breakup of particularly massive nuclei through fission, but also through the combination of small nuclei to form larger ones, nuclear fusion. In fact, from Aston's studies it could be seen that, mass for mass, nuclear fusion would produce far more energy than nuclear fission. This was particularly true in the conversion of hydrogen to helium. That is, the conversion of the individual protons of 4 separate hydrogen nuclei into the 2-proton, 2-neutron structure of the helium nucleus. A gram of hydrogen undergoing fusion to helium would deliver some 15 times as much energy as a gram of uranium undergoing fission. As early as 1920, the English astronomer Arthur Stanley Eddington 1882 to 1944, had speculated that the sun's energy might be derived from the interaction of subatomic particles. Some sort of nuclear reaction seemed, by then, to be the most reasonable way of accounting for the vast energies constantly being produced by the sun. The speculation became more plausible with each year. Eddington himself studied the structure of stars, and by 1926 had produced convincing theoretical reasons for supposing that the center of the sun was at enormous densities and temperatures. A temperature of some 15 million to 20 million degrees centigrade seemed to characterize the sun's center. At such temperatures, atoms could not exist in earthly fashion. Held together by the sun's strong gravitational field, they collided with such energy that all or almost all their electrons were stripped off, and little more than bare nuclei were left. These bare nuclei could approach each other much more closely than whole atoms could, which was why the center of the sun was so much more dense than earthly matter could be. The bare nuclei, smashing together at central sun temperatures, could cling together and form more complex nuclei. Nuclear reactions brought about by such intense heat, millions of degrees, are called thermonuclear reactions. As the 1920s progressed, further studies of the chemical structure of the sun showed it to be even richer in hydrogen than had been thought. In 1929, the American astronomer Henry Norris Russell, 1877 to 1957, reported evidence that the sun was 60% hydrogen in volume. Even this was too conservative. 80% is considered more nearly correct now. If the sun's energy were based on nuclear reactions at all, then it had to be the result of hydrogen fusion. Nothing else was present in sufficient quantity to be useful as a fuel. More and more was learned about the exact manner in which nuclei interacted and about the quantity of energy given off in particular nuclear reactions. It became possible to calculate what might be going on inside the sun by considering the densities and temperatures present, the kind and number of different nuclei available, and the quantity of energy that must be produced. In 1938, the German-American physicist Hans Albrecht Bethe, born 1906, and the German astronomer Carl Friedrich von Weizsäcker, born 1912, independently worked out the possible reactions, and hydrogen fusion was shown to be a thoroughly practical way of keeping the sun going. Thanks to the high rate of energy production by thermonuclear reactions, and to the vast quantity of hydrogen in the sun, not only has it been possible for the sun to have been radiating energy for the last 5 billion years or so, but it will continue to radiate energy in the present fashion for at least 5 billion years into the future. Even so, the sheer quantity of what is going on in the sun is staggering in earthly terms. In the sun, 650 million tons of hydrogen are converted into helium every second, and the process each second sees the disappearance of 4,600,000 tons of mass. Thermonuclear bombs. Could thermonuclear reactions be made to take place on Earth? The conditions that exist in the center of the sun would be extremely difficult to duplicate on the Earth, so there was a natural search for any kind of nuclear fusion that would produce similar energies to those going on in the sun, but which would be easier to bring about. There are 3 hydrogen isotopes known to exist. Ordinary hydrogen is almost entirely hydrogen-1, with a nucleus made up of a single proton. Small quantities of hydrogen-2, deuterium, with a nucleus made up of a proton plus a neutron, also exist, and such atoms are perfectly stable. In 1934, Rutherford, along with the Australian physicist Marcus Lawrence Elwin Oliphant, born 1901, and the Austrian chemist Paul Hartek, born 1902, sent hydrogen-2 nuclei flying into hydrogen-2 targets and formed hydrogen-3, also called tritium from the Greek word for third, with a nucleus made up of a proton plus 2 neutrons. Hydrogen-3 is mildly radioactive. Hydrogen-2 fuses to helium more easily than hydrogen-1 does, and, all things being equal, hydrogen-2 will do so at lower temperatures than hydrogen-1. Hydrogen-3 requires lower temperatures still, but even for hydrogen-3 it still takes millions of degrees. Hydrogen-3, although the easiest to be forced to undergo fusion, exists only in tiny quantities. Hydrogen-2, therefore, is the one to pin hopes on, especially in conjunction with hydrogen-3. Only 1 atom out of every 6,000 hydrogen atoms is hydrogen-2, but that is enough. There exists a vast ocean on Earth that is made up almost entirely of water molecules, and in each water molecule, 2 hydrogen atoms are present. Even if only 1 in 6,000 of these hydrogen atoms is deuterium, that still means there are about 35,000 billion tons of deuterium in the ocean. What's more, it isn't necessary to dig for that deuterium or to drill for it. If ocean water is allowed to run through separation plants, the deuterium can be extracted without very much trouble. In fact, for the energy you could get out of it, deuterium from the oceans extracted by present methods and without allowing for future improvement would be only 1/100th as expensive as coal. The deuterium in the world's ocean, if allowed to undergo fusion little by little, would supply mankind with enough energy to keep us going at the present rate for 500 billion years. To be sure, to make deuterium fusion practical, it may be necessary to make use of rarer substances, such as the light metal lithium. This will place a sharper limit on the energy supply, but even if we are careful, fusion would probably supply mankind with energy for as long as mankind will exist. Then, too, there would seem to be no danger of hydrogen fusion plants running out of control. Only small quantities of deuterium would be in the process of fusion at any one time. If anything at all went wrong, the deuterium supply could be automatically cut off, and the fusion process, with so little involved, would then stop instantly. Moreover, there would be less reason to worry about atomic wastes, for the most dangerous products, hydrogen-3 and neutrons, could be easily taken care of. It seems ideal, but there is a catch. However clear the theory, before a fusion power station can be established, some practical method must be found to start the fusion process, which means finding some way for attaining temperatures in the millions of degrees. One method for obtaining the necessary temperature was known by 1945. An exploding fission bomb would do it. If somehow the necessary hydrogen-2 was combined with a fission bomb, the explosion would set off a fusion reaction that would greatly multiply the energy released. You would have, in effect, a thermonuclear bomb. To the general public, this was commonly known as a hydrogen bomb or an H-bomb. In 1952, the first fusion device was exploded by the United States in the Marshall Islands. Within months, the Soviet Union had exploded one of its own, and in time, thermonuclear bombs, thousands of times as powerful as the first fission bomb over Hiroshima, were built and exploded. All thermonuclear bombs have been exploded only for test purposes. Even testing seems to be dangerous, however, at least if it is carried on in the open atmosphere. The radioactivity liberated spreads over the world and may do slow but cumulative damage. Controlled fusion. However effective a fusion bomb may be in liberating vast quantities of energy, it is not what one has in mind when speaking of a fusion power station. The energy of a fusion bomb is released all at once, and its only function is that of utter destruction. What is wanted is the production of fusion energy at a low and steady rate, a rate that is under the control of human operators. The Sun, for instance, is a vast fusion furnace 866,000 miles across, but it is a controlled one, even though that control is exerted by the impersonal laws of nature. It releases energy at a very steady and very slow rate. The rate is not slow in human terms, of course, but stars sometimes do release their energy in a much more cataclysmic fashion. The result is a supernova, in which for a short time a single star will increase its radiation as much as 1 trillion times its normal level. The Sun or any star going at its normal rate is controlled and steady in its output because of the advantage of huge mass. An enormous mass composed mainly of hydrogen compresses itself through its equally enormous gravitational field into huge densities and temperatures at its center, thus igniting the fusion reaction, while the same gravitational field keeps the Sun together against its tendency to expand. There is, as far as scientists know, no conceivable way of concentrating a high gravitational field in the absence of the required mass, and the creation of controlled fusion on Earth must therefore be done without the aid of gravity. Without a huge gravitational force, we cannot simultaneously bring about sun-center densities and sun-center temperatures. One or the other must go.
On the whole, it would take much less energy to aim at the temperatures than at the densities, and would be much more feasible. For this reason, physicists have been attempting all through the nuclear age to heat thin wisps of hydrogen to enormous temperature. Since the gas is thin, the nuclei are farther apart and collide with each other far fewer times per second. To achieve fusion ignition, therefore, temperatures must be considerably higher than those at the center of the Sun. In 1944, Fermi calculated that it might take a temperature of 50 million degrees to ignite a hydrogen-3 fusion with hydrogen-2 under earthly conditions, and 400 million degrees to ignite hydrogen-2 fusion alone. To ignite hydrogen-1 fusion, which is what goes on in the Sun, at a mere 15 million degrees, physicists would have to raise their sights to beyond the billion-degree mark. This would make it seem almost essential to use hydrogen-3 in one fashion or another. Even if it can't be prepared in quantity to begin with, it might be formed by neutron bombardment of lithium, with the neutrons being formed by the fusion reaction. In this way, you would start with lithium and hydrogen-2 plus a little hydrogen-3. The hydrogen-3 is formed as fast as it is used up. Although in the end hydrogen is converted to helium in a controlled fusion reaction, as in the Sun, the individual steps in the reaction under human control are quite different from those in the Sun. Still, even the temperatures required for hydrogen-3 represent an enormous problem, particularly since the temperature must not only be reached but must be held for a period of time. You can pass a piece of paper rapidly through a candle flame without igniting it. It must be held in the flame for a short period to give it a chance to heat and ignite. The English physicist John David Lawson, born 1923, worked out the requirements in 1957. The time depended on the density of the gas. The denser the gas, the shorter the period over which the temperature had to be maintained. If the gas is about 100,000 times as dense as air, the proper temperature must be held under the most favorable conditions for about 1/1000th of a second. Eventually, such devices were built and called stellarators, from the Latin word for star, because it was hoped that it would produce the conditions that would allow the sort of fusion reactions that went on in stars. All through the 1950s and 1960s, physicists have been slowly inching toward their goal, reaching higher and higher temperatures and holding them for longer and longer periods in denser and denser gases. In 1969, the Soviet Union used a device called Tokamak-3, a Russian abbreviation for their phrase for electric magnetic, to keep a supply of hydrogen-2 a millionth as dense as air in place while heating it to tens of millions of degrees for 1/100th of a second. A little denser, a little hotter, a little longer, and controlled fusion might become possible. Beyond fusion. Antimatter. Is there anything that lies beyond fusion? When hydrogen undergoes fusion and becomes helium, only 0.7% of the original mass of the hydrogen is converted to energy. Is it possible to take a quantity of mass and convert all of it, every bit, to energy? Surely that would be the ultimate energy source. Mass for mass, that would deliver 140 times as much energy as hydrogen fusion would. It would be as far beyond hydrogen fusion as hydrogen fusion is beyond uranium fission. And, as a matter of fact, total annihilation of matter is conceivable under some circumstances. In 1928, the English physicist Paul Adrien Maurice Dirac, born 1902, presented a treatment of the electron's properties that made it appear as though there ought also to exist a particle exactly like the electron in every respect except that it would be opposite in charge. It would carry a positive electric charge exactly as large as the electron's negative one. If the electron is a particle, this suggested positively charged twin would be an antiparticle. The prefix comes from a Greek word meaning opposite. The proton is not the electron's antiparticle. Although a proton carries the necessary positive charge that is exactly as large as the negative charge of the electron, the proton has a much larger mass than the electron has. Dirac's theory required that the antiparticle have the same mass as the particle to which it corresponded. In 1932, C.D. Anderson was studying the impact of cosmic particles on lead. In the process, he discovered signs of a particle that left tracks exactly like those of an electron, but tracks that curved the wrong way in a magnetic field. This was a sure sign that it had an electric charge opposite to that of the electron. He had, in short, discovered the electron's antiparticle, and this came to be called the positron. Positrons were soon detected elsewhere, too. Some radioactive isotopes formed in the laboratory by the Joliet-Curies and by others were found to emit positive beta particles, positrons rather than electrons. When an ordinary beta particle or electron was emitted from a nucleus, a neutron within the nucleus was converted to a proton. When a positive beta particle, a positron, was emitted, the reverse happened. A proton was converted to a neutron. A positron, however, does not endure long after formation. All about it were atoms containing electrons. It could not move for more than a millionth of a second or so before it encountered one of those electrons. When it did, there was an attraction between the two, since they were of opposite electric charge. Briefly, they might circle each other to form a combination called positronium, but only very briefly. Then they collided, and, since they were opposite, each canceled the other. The process whereby an electron and a positron met and canceled is called mutual annihilation. Not everything was gone, though. The mass, in disappearing, was converted into the equivalent amount of energy, which made its appearance in the form of one or more gamma rays. It works the other way, too. A gamma ray of sufficient energy can be transformed into an electron and a positron. This phenomenon, called pair production, was observed as early as 1930, but was only properly understood after the discovery of the positron. Of course, the mass of electrons and positrons is very small, and the amount of energy released per electron is not enormously high. Still, Dirac's original theory of antiparticles was not confined to electrons. By his theory, any particle ought to have some corresponding antiparticle. Corresponding to the proton, for instance, there ought to be an antiproton. This would be just as massive as the proton and would carry a negative charge just as large as the proton's positive charge. An antiproton, however, is 1,836 times as massive as a positron. It would take gamma rays, or cosmic particles, with 1,836 times as much energy to form the proton-antiproton pair as would suffice for the electron-positron pair. Cosmic particles of the necessary energies existed, but they were rare, and the chance of someone being present with a particle detector, just as a rare super-energetic cosmic particle happened to form a proton-antiproton pair, was very small. Physicists had to wait until they had succeeded in designing particle accelerators that would produce enough energy to allow the creation of proton-antiproton pairs. This came about in the early 1950s, when a device called the Cosmotron was built at Brookhaven National Laboratory in Long Island in 1952, and another called the Bevatron at the University of California in Berkeley in 1954. Using the Bevatron in 1956,
Segre, the discoverer of technetium who had by that time emigrated to the United States, the American physicist Owen Chamberlain, born 1920, and others succeeded in detecting the antiproton. The antiproton was as unlikely to last as long as the positron was. It was surrounded by myriads of proton-containing nuclei, and in a tiny fraction of a second it would encounter one. The antiproton and the proton also underwent mutual annihilation, but having 1,836 times the mass, they produced 1,836 times the energy that was produced in the case of an electron and a positron. There was even an antineutron, a particle reported in 1956 by the Italian-American physicist Oreste Piccioni, born 1915, and his co-workers. Since the neutron has no charge, the antineutron has no charge either, and one might wonder how the antineutron would differ from the neutron then. Actually, both have a small magnetic field. In the neutron, the magnetic field is pointed in one direction with reference to the neutron's spin. In the antineutron, it is pointed in the other. In 1965, the American physicist Leon Max Lederman, born 1922, and his co-workers produced a combination of an antiproton and an antineutron that together formed an antideuteron, which is the nucleus of antihydrogen 2. This is good enough to demonstrate that if antiparticles existed by themselves, without the interfering presence of ordinary particles, they could form antimatter, which would be precisely identical with ordinary matter in every way, except for the fact that electric charges and magnetic fields would be turned around. If antimatter were available to us, and if we could control the manner in which it united with matter, we would have a source of energy much greater and perhaps simpler to produce than would be involved in hydrogen fusion. To be sure, there is no antimatter on Earth, except for the submicroscopic amounts that are formed by the input of tremendous energies. Nor does anyone know of any conceivable way of forming antimatter at less energy than that produced by mutual annihilation, so that we might say that mankind can never make an energy profit out of it, except that, with the memory of Rutherford's prediction that nuclear energy of any kind could never be tapped, one hesitates to be pessimistic about anything. The unknown. Physical theory makes it seem that particles and antiparticles ought to exist in the universe in equal quantities. Yet on Earth, and we can be quite certain in the rest of the solar system, and even very likely in the rest of the galaxy, protons, neutrons, and electrons are common, while antiprotons, antineutrons, and positrons are exceedingly rare. Could it be that when the universe was first formed there were indeed equal quantities of particles and antiparticles, but that they were somehow segregated, perhaps into galaxies and anti-galaxies? If so, there might occasionally be collisions of a galaxy and an anti-galaxy, with the evolution of vast quantities of energy as mutual annihilation on a cosmic scale takes place. There are, in fact, places in the heavens where radiation is unusually high in quantity and in energy. Can we be witnessing such enormous mutual annihilation? Indeed, it is not altogether inconceivable that we may still have new types of forces and new sources of energy to discover. Until about 1900, no one suspected the existence of nuclear energy. Are we quite sure now that nuclear energy brings us to the end, and that there is not a form of energy more subtle still, and greater? In 1962, for instance, certain puzzling objects called quasars were discovered far out in space, 1 billion light-years or more away from us. Each one shines from 10 to 100 times as brilliantly as an entire ordinary galaxy does, and yet may be no more than 100,000th as wide as a galaxy. This is something like finding an object 10 miles across that delivers as much total light as 100 suns. It is very hard to understand where all that energy comes from and why it should be so concentrated into so tiny a volume. Astronomers have tried to explain it in terms of the 4 interactions now known, but is it possible that there is a 5th greater than any of the 4? If so, it is not impossible that eventually man's restless brain may come to understand and even utilize it. End of Section 6. End of Worlds Within Worlds. The Story of Nuclear Energy by Isaac Asimov.